co-host, so you can mute, unmute people.
Yes, for sure. Yes. So, oh, hello, Ray. Nice to see you. Can you hear me?
Yes, I can. Can you hear me?
Yes, yes. Great. Great to see you after a long, long time.
It's been way too long. I agree with you.
Yeah, true, true.
Are you well?
Fine. And how are you? And your
Very
family?
well, thank you.
Okay, great. So I expect to have some free time for us to talk to you. And
Excellent.
let's see.
Excellent.
Okay, great. So actually, I will unmute myself for a while and then I will be back again.
All right, very good.
Asking me to unmute, why? Vijaya, there is no need of unmuting me.
It's okay, okay, don't worry about it.
I will unmute myself.
So, yeah,
okay?
you have that option, you can unmute yourself.
I will unmute.
are we ready to start? Vijay, we are ready to start.
Yeah. So I was waiting for Professor Das, but I don't know why he
He
did
is
not
there.
join. So I'll just.
He's there. He has
Huh?
joined. He has joined.
Oh, yeah, yeah.
Maybe I can start now. It's fine. So very good morning to all dignitaries, esteemed speakers, participants, organizing committee, and all our audience from across the nation and abroad who have joined us with the inaugural session of Fundamental Science and Quantum Technologies using Atomic System, FSQT 2020. I'm Dr. Bindya Arora, and I welcome you all on behalf of FSQT. The conference aims to honor Professor Bhanu Pratap Das on his 65th birthday. The goal of the meeting is to impart vital awareness pertaining to important research topics that are of current interest in atomic and molecular physics in an interactive manner. It's a privilege to have amongst us Professor Anil Bhardwaj, Director of Physical Research Laboratory, Ahmedabad, as our chief guest for the day, and Professor Debashish Mukherjee, Distinguished Professor at PCG CRIST, who is the chair of FSQT. The COVID pandemic came in most unpredictable form and has rendered the entire system ineffective. And the entire education system is now resorting to online measures. In order to keep up the learning momentum,
कब से?
PRL Ahmedabad and Cyrox Science Club GNDU to embrace the approach and put a firm foot forward by organizing this conference, which is happening in virtual mode. A number of talks will be delivered by eminent speakers in this 4-day conference, covering topics not limited to fundamental physics using atoms and molecules, light matter interaction, quantum information and computation, but many more. So it's a pleasure to have Professor Debashish Mukherjee, Chair FSQT, with us on this occasion. And Professor Mukherjee, as we know, is a well-known internationally for his research in the fields of molecular many-body theory, theoretical spectroscopy, finite temperature, non-perturbative many-body theories. He is a fellow of International Academy of Quantum Molecular Science and is the recipient of the prestigious Humboldt Prize. He was also awarded the prestigious Fukui Medal named after the Nobel Prize winner, Kenshi Fukui. He is the first theoretical chemist from India to be conferred with this distinction. So it's an honor, sir, to have you here. He is a fellow of the International Academies of Sciences and of the World Academy of Sciences. He has many other honors and awards to his credit. And the list is really very long if I just continue for the entire day. And it includes briefly the Shanti Swarup Bhatnagar Prize from the Council of Scientific and Industrial Research India, Jagdish Shankar Medal Award, and Southern Basu Memorial Award in Chemistry from the Indian National Science Academy. So I welcome you, sir. And without any further ado, I would now request our chair, Professor Mukherjee, to brief us about FSQT and introduce our esteemed chief guest for the day.
Many thanks, India, for this kind and generous introduction. Good morning to everybody. And I have this pleasant duty of not only welcome you all, but also to introduce the chief guest of our conference, Dr. Anil Bhardwaj. Dr. Bhardwaj completed his master's in physics from Lucknow University and received his PhD in applied physics, specializing in planetary and space science from the Indian Institute of Technology, Banaras Hindu University. He has been associated with ISRO as we call it, since then, including holding important positions such as the head of the planetary science branch, the director of the Space Physics Lab in Vikram Sarabhai Space Center, Trivandrum, and since 2017, he is the director of the Physical Research Lab, Ahmedabad, the major host of this particular meeting. His research interests include theoretical and observational studies of planetary surfaces, atmospheres, and their coupling with magnetospheric plasma and solar wind. He has several publications, quite a lot, in reputed journals. He has been the editor-in-chief of several books, and he held guest editorships in several journals. He also wrote several general articles and delivered quite a lot of public lectures for popularizing science. He had been the principal investigator of the experiments on the famous Chandrayaan-1 Mars orbital mission, Chandrayaan-2 missions, and has been a co-investigator in the important planetary observation with the GMRT telescope, Chandra and XMM Newton Observatory, the Hubble Space Telescopes for ultraviolet observation, the NASA IRTF and GMRT for infrared observations, and other observations, including several multi-wavelength activity. His awards and honors include the Shanti Swarup Bhatnagar Prize, ISRO Team Excellence Award for the Chandrayaan-1 mission, ISRO Merit Award, Infosys Prize in Physical Science, and the letter of felicitation by the Uttar Pradesh state government for distinguished work in science and technology. So it's a pleasure and a privilege to welcome Dr. Bhanu. May I request him to kindly address the assembled guests.
Thank you, Professor Devashish Mukherjee. Thanks to the organizers of this conference and to my colleague, Dr. Vijaya Sahu, for inviting me for this inaugural ceremony. Namaskar, very good morning, and a warm welcome to all the participants, speakers of key talk, invited talks, contributed talk, posters, and all the viewers and listeners from all over the world joining us live on Zoom as well as on YouTube to this 4-day international webinar on fundamental science and quantum technologies using atomic systems, or in short, FQST 2020. This is conference being hosted by PRL, and I would have loved to meet you all in person in Ahmedabad and greet you in the campus of PRL. But the prevailing situation in the country and around the world of COVID pandemic has made us to join us live on this way. PRL, as you all know, has a glorious history of 7 decades of excellence in science, particularly fundamental science, founded by Dr. Vikram Sarabhai in the year 1947 at the age of 28. PRL has been very actively working in the domains of atomic and molecular physics. This international webinar is very special on 2 occasions or 2 reasons. One, that we have just completed the birth centenary celebration of Dr. Vikram Sarabhai, the founder of PRL and the father of Indian space program. Secondly, we are cherishing and celebrating the 65 years of Professor Bhanu Pratap Das, a renowned and well-known atomic molecular physicist, and we will be doing that felicitation probably on the last day. The theme of this meeting is very apt, talking about fundamental science and quantum technologies, including, of course, the fundamental physics of atomic and molecular physics, light and matter interactions, or quantum science, quantum technology, quantum information, quantum computing, as well as talking about what you call relativistic many-body methods, atomic clocks, and steady state art of various experiments which is conducted on the basis of the theories which is developed by many groups. I know many leading theorists and experimentalists are joining in this 4 days conference. And this would be a good platform for people to listen to the talks, as well as to foster discussion and interactions and develop linkages to carry forward this field in future. I thank the members of the Scientific Organizing Committee for putting together a very excellent program. I can see experts delivering talks in very exciting topics. There are about more than 40 talks being delivered in this conference, and about 400 participants have already registered for taking part in this conference. So this really shows the enthusiasm among the delegates and participants joining us in this meeting. I'm extremely delighted and honored to declare the FQST 2020 open for scientific deliberations. I also thank the technical committee, the members of technical committees who are taking care of this online webinar, for making this webinar very useful, fruitful, and seamlessly uninterrupted. It would be really highly fulfilling for all of us to have this conference in this way in the current situation of pandemic. And this also provides us the opportunity of many more who could not travel otherwise to attend these conferences to take part and listen to the exciting talks being organized by the Scientific Organizing Committee. So I take this opportunity to welcome you all once again to this conference, and I wish the conference a grand success. Thank you. Dhanyavad.
Thank you very much, Dr. Bhardwaj, for your kind inaugural talk. I see Professor Bhanu Das, Bhanu as we all fondly call him, is present, and I welcome him very cordially to the conference that is being held in his honor. So we begin our scientific sessions. Thanks a lot, Dr. Bhardwaj, for coming. We begin the scientific session. It should have started at about 10:15, so we had some time. But let me take this opportunity of reminding all the speakers that the 45-minute duration talks actually would take 35 minutes of the presentation, followed by 10 minutes of discussion. And the 30-minute talks would have 25 minutes of the talk and 5 minutes of discussion. And I request all the speakers to kindly stick to the time schedule. It's otherwise extremely difficult to manage as the conference goes on. I would also request the questioners to keep their questions just to one. And please use the chat mode to send us the questions. You should not leave it till the end of the talk, but if you feel that you have a question, kindly just send it, and our resource persons will be keeping track of them, and then I will actually select a few. I cannot select all, so I will leave it to the speakers to talk about them. Than the time can allow, we will send them to the respective speakers. So I think with that, let us begin the first scientific session. And the first speaker
Mr. Mukherjee, I'm sorry to
of
interrupt.
the session.
I'm sorry to interrupt you. I just want to make a short announcement that
Please.
the participants who have joined us on YouTube, they can also ask questions by typing their questions on the YouTube chat window. Okay, thank you so much, Professor Mukherjee. Please continue.
Yeah, so I'm unmuting. So I'm not able to unmute Dr. Mahanti, and after I unmute, I will request him to take chair. Okay, thanks a lot. So it's a pleasure to invite Professor Subhendra Mahanti, and he is going to talk on the detection of dark matter with atomic transitions. And he is an old friend of Professor Das, so it's a pleasure to inaugurate the meeting with a talk by Professor Mahanti. Professor Mahanti, please.
Right. Thank you, Professor Mukherjee. And let me share the screen. Is the screen visible?
No, sir.
No?
No?
Well, I mean, not from my side. So maybe Bindia might help us here.
Yeah, now it is.
Now it's coming. Yeah.
Okay. So let me start by thanking the organizers and especially Vijay Sahu for giving me this honor. And it's indeed a great pleasure that I am speaking on the occasion of 65th birthday of Professor Bhanu Das. Now, Bhanu and I go back a long way. He's an old friend. So it's a great pleasure that I'll be part of this occasion. I remember we celebrated his 60th birthday also in PRL, and that was a physical meeting, which is always better, but nevertheless. So hello, Bhanu, how are you? And let me start by, so I'll be talking about dark matter detection with atoms. So this is basically doing some physics beyond the standard model. Something that we know from standard model is all well known by now, including the discovery of the Higgs boson in 2012. So what's unknown are things like dark matter. What's the nature of dark matter? If there are any other particles beyond standard model? What is the gauge group beyond standard model? If there is a unification of the gauge groups and so on. And normally we associate these all these experimental efforts with colliders. Okay. But there is a big sector which is dark matter, and those are things which are, so dark matter is a part where the discovery effort is in underground laboratories using low energy physics, not high energy physics. So this is something which we go beyond standard model, and I'm sure since you're all experts in this atomic physics, you know that Bhanu Das was the pioneer in trying to test the standard model. When the standard model started, the neutral current, the parity violation associated with neutral currents, he was the pioneer in trying to calculate that trying to see that in atomic systems. So it's indeed fitting that now that standard model is well established, I mean, he's still in the forefront of using atomic systems to go beyond standard model. Okay. So I'll start by, okay. So I'll be talking about dark matter. Now, dark matter is, so as this pie chart on the left shows, if you take the composition of the universe, the energy density of the universe or the matter in the universe, 69% of that is in the form of what's called dark energy. So that's also called the cosmological constant. That's a sort of a very exotic matter where when the space expands, the matter does not dilute. That's why it's called a cosmological constant. And that also is responsible for the accelerated expansion of the universe. Other than that, we have atomic matter, the matter that we are all made of, that composes the stars and the luminous part of the universe that we observe. That's only about 5%. The other 25% is dark matter. Now, the dark matter is something, it is not exotic matter like dark energy, but it behaves, as far as gravity is concerned, it behaves like our normal matter in the sense that when the universe expands, the dark matter dilutes just like ordinary matter. So it is like ordinary matter, except that it does not have interactions with photons. So it is non-luminous. So when I say interaction with photon, it is a very feeble interaction with photon. It does not have a charge like the electron and the proton. It has very feeble interaction with photons, and I'll specify later what I mean by feeble interactions. And there are also neutrinos which have a mass, which are 0.1% of the universe. That's the neutrino mass. Then there are photons. Also, they have energy, the 3-degree microwave photon. And this picture that you see is anisotropy in the 3 degrees. So there are fluctuations when you look at different directions in the sky. There are fluctuations in the 3 degree in 1 part in 10 to the minus 5. And those fluctuations, when you study them carefully, actually tell us this whole pie chart that I just discussed. They come from observations of this CMB anisotropy. And that was carried out using this COBE, WMAP, and Planck satellites. Okay. And we have, LIGO has shown us that there are black holes. So they constitute about 0.005% of the universe. So they are not, as far as we can tell right now, they are not the dark matter, but this whole dark sector is unknown. So we may have surprises in all of these, because none of these are actually, we know what is the composition, but we don't know what they actually are made of. Now I'll go to this dark matter at the scale of galaxies. In galaxies, one can plot this rotation curve. So one can, by observing the Doppler shift of stars, and also looking at the hydrogen atom and the 21 centimeter line from the, which comes from the hyperfine transition of the hydrogen atom, one can tell the velocity of this gas and the stars, and one can plot the velocity versus distance from the center of the galaxy, the rotational velocity. And normally you would expect that the gas and the stars are kept in place by the centripetal acceleration from the matter in the center. Now the luminous matter in the center would give you a rotational velocity, which is shown by this dashed line. Okay. But what is observed is this, the line above. So the fact that this rotational velocity is constant or actually grows slightly sometimes tells us that there is a lot more matter than what is seen in the visible sector, even in the galaxies. So we already saw that dark matter exists in the cosmological scales. It's also there in the galactic scale. So about 95% or more matter in the galaxy is actually in the form of dark matter. So this is a rotation curve of M33 galaxy, and this is seen in most galaxies, that there is a discrepancy between what you observe from the visible matter and what is actually seen. Now this is the rotation curve of our Milky Way galaxy. Now the thing with Milky Way, since we are inside the galaxy, it's more difficult to observe, which is why you see all this dispersion in the observations. So we are at this 8.3 kiloparsec from the center. This is the location of the sun. Now fitting the rotation curve with the mass, the density distribution of the dark matter, which will give you this rotation curve, we infer that the density of dark matter at this location of the sun is 0.4 GeV per centimeter cube. So in terms of mass, it is 0.4 GeV by c square per centimeter cube. So proton mass is 1 GeV per c square. So this is about like more than 1/3 of a proton mass per centimeter cube of dark matter exists everywhere here on Earth and in the location of the sun. So if there is this much dark matter at the location of the Earth and everywhere around us, one should be able to detect it somehow. because they should be just like other particles, like neutrinos, for instance, which have they only have weak interactions, but still they can scatter other particles, and neutrinos have been detected by causing transitions in other particles, in the particles that we see. So similarly, there is a big effort to detect dark matter. So schematically, the effort in detecting dark matter is carried out. I'll show you a little more detail in next transparencies, but in the next slides. But schematically, what is expected is the following. WIMPs are what is called weakly interacting massive particles. So this was what was the paradigm for dark matter, that they are very massive compared to neutrons and protons. But that picture has now changed, and I'll be talking mostly about how this WIMP picture has changed now. But this is the standard picture, that you have weakly interacting massive particles that 10 to 100 times mass of the neutrons and protons. And what they will do is that they will scatter the nuclei, because their Compton wavelength is of the size of the nuclei. So they have coherent, they will scatter all the nucleons coherently. So they will see the nucleus as a whole, whereas they will scatter the electrons individually. So there is a great enhancement in the scattering cross section of the nuclei compared to the scattering cross section of with electrons. In addition, if the mass of the dark matter is about 10 to 100 GeV, then using heavy nuclei like argon and xenon, which are again 100 GeV nuclei, they will be the most efficient transfer of energy from this dark matter to the nucleus. So this was the effort, that you take a lot of xenon, for instance, in a tank, put it underground to shield it from cosmic rays, and then see if the xenon atoms are scattered. If the atoms or nuclei are scattered, they pass on the energy to the lattice, and there is a scintillation. And from the scintillation, by observing the scintillation in the xenon tank of xenon, one was expecting to see dark matter. Now, a little more bit of just numbers of what you expect. If you have, so I'll go through this very quickly. The recoil energy, when a nucleus is hit by a dark matter, the recoil energy is given by this, where this cos theta is the angle of scattering between the nuclei and the dark matter, and this mu is the reduced mass. And if you take the mass of the WIMP, that is this dark matter, to be about 100, the WIMP velocity, which this we get from the rotation curve, this is about 200 kilometers per second. And if you take this target, the nucleus which is observing the dark matter, the target to be argon, let's say, which is 40 GeV per centimeter square, then the recoil energy is about 100 keV. So the dark matter imparts a energy to the nucleus of about 100 keV. Okay, so that energy should be seen in terms of the the scintillation provided by the nucleus. In addition, the scattering rate is given by, in the scattering rate, one adds up so the dark matter actually interacts with the quarks, but from the quarks you go to the nucleon. So in the end, the scattering rate is given by some expression of this kind, where it's proportional to the atomic number as well as the atomic mass, A, and the square of this. So this is what we called the scattering is coherent. That's why it becomes the square of the total atomic number. Whereas if it was incoherent, then it will not be the square, it will be just proportional to the atomic number. Or if it is only coupling to the charge, it will just be proportional to the charge. But the square is where you have, because of the coherent scattering. And this was the reason why this first choice for observing this dark matter was this heavy nuclei. Because if you have a of 100, then you get a square, 100 times benefit in the scattering cross section or the scattering rate by taking heavy atoms. So schematically, there are many experiments, and I'll be discussing one famous experiment called xenon 1 ton, which is currently the most sensitive experiment for detecting dark matter. So what's happening in that experiment is that you have a tank full of liquid xenon. So you have a dark matter particle which comes and hits the xenon. It imparts energy to the nuclei, and that keV energy can also ionize the electrons. So you will see two signals. One is the signal S1, which is just the scintillation which is picked up by the photodetectors all around. So the light coming from the scintillation when the nucleus is hit. Secondly, these electrons travel in an electric field, and then they are collected at the ends. So there is this second signal where the electrons are collected, and by coordinating, by seeing that this S2 signal actually is well coordinated with the S1, we know that they came from the same event. So one look for this correlation between the S1 and S2, and if there is a correlation in these two, then that is what we say that the dark matter, that's a signal for dark matter. Most of the time what happens on the other hand is basically the background, the cosmic rays or the radon or the background radiation in the laboratory, that causes a sort of ionization of the xenon, and you only see the S2 signal without the S1 signal. So basically that is the background, or that was the standard picture, that the background is just the electrons, whereas the signal is just the scintillation of the nucleus. But so far there is no signal where there is a correlation between this S1 and S2. There is no nuclear scattering seen, although we see a lot of this electrons which are collected. So the first conclusion was, yeah. So this is a picture of this xenon 1 ton. So there is actually 2 tons of xenon in this, of which 1 ton is active area from which the observations are taking place. So you can see this is a big tank of xenon, and this is where all the other auxiliary equipment lies. So you can see the scale of this experiment. And this is in Gran Sasso laboratory in Italy. It's an underground lab under a mountain which actually shields it from cosmic ray background. Okay, so as I said, there is nothing seen so far. So all we get is an exclusion plot of the cross section of the dark matter nucleon. So this is the cross section in centimeter square, and versus the mass of the dark matter. And successive experiments have lowered this. So these curved lines are the exclusion regions. That means all the cross section and mass above these curves are ruled out. So the current limit is this green band. This is a 1 sigma band, and the yellow band is a 2 sigma band. This is the xenon 1 ton experiment. Okay. And you can see that the cross section has gone down to 10 to the minus 46 for 100 GeV dark matter mass. Now, this sensitivity of this experiment falls off when the dark matter mass goes down. It also falls off, so it goes down when the dark matter mass is small. There is not enough kinetic energy in the dark matter to scatter a xenon nucleus. So for instance, if it's a 1 GeV or a MeV dark matter, then you will not see it in this experiment, although the dark matter may be there in abundance. This experiment will not be able to pick it up. So one says, well, okay, so far we have not seen dark matter in this WIMP mass range, massive particle range. Let us look for dark matter in the MEV range. Maybe the dark matter is in the MEV region. So in that case, the strategy of your search has to change. And one goes to the following. So if you have a 1 MeV dark matter, okay, or lower mass dark matter, then the most transfer kinematically, the most efficient transfer of energy is by a particle if it hits a particle of a similar mass. So in our hands we have electrons. So if you have a MeV particle and the electron is 0.5 MeV mass, if there is a scattering of a free electron, you'll see some energy imparted to the electrons, and that would be, so if you have free electrons or electrons in a metal or in a semiconductor, you can see if there is a sudden transition in the electron energy, then that would be a sign that you have shielded it from all the background, and still if there is a transition in the electron energy, that would be the sign of a dark matter scattering. So sorry, here I'm showing the electron in a, so this would be elastic scattering if it's a free electron. However, if you have bound electrons, like for instance in the xenon atom, so two things can happen. You can have a transition from a lower shell to the upper shell of xenon, and followed by a electromagnetic transition from the upper shell to lower shell, which is seen by the detectors. So if you are having a xenon tank sitting there, and all at the atoms are expected at the ground state, and suddenly you see a transition from the upper shell to the lower shell, that would be the sign of a dark matter induced transition. What can also happen, since as I said, these dark matter carry about keV energy or so, that you can have a ionization of the electrons from this xenon atom. So the dark matter scatters goes away, and it imparts energy, such energy that the electron exits the atom, and these free electrons can then be observed. So this would be the S2 signal that I was discussing. So now if you have a S2 signal and only without the S1, and you have controlled the background, that you know this radion, the radon and all the cosmic rays you have well in control, then just by observing S2, you can observe the electron scattering. So once the nuclear scattering sort of did not give any result, people are concentrating on this S2 signal, the scattering of the electrons. And yeah, I'll so I will show you the recent June 2020 Xenon 1 ton announced that it is seeing an excess over what is observed. So now the thing is that why would a dark matter, what are the physics of this dark matter that it can scatter electrons in the xenon, which is seen. So this was an announcement that you see an excess of what is this red line, which is the background, which is seen. So one model, for instance, of dark matter, okay, was that dark matter has anapole moment, electromagnetic, it has very small charge, but it can have other electromagnetic form factors. For instance, it can have an anapole moment, the dark matter. It can also have a magnetic dipole moment like the like the electron, or it could have an electric dipole moment, which the electron might have if there is a CP violation. So there are these form factors which can be there for with the dark matter. And so basically the dark matter will emit a photon which will scatter. So through the exchange of a photon, the dark matter can scatter an electron if it has one of these electromagnetic form factors. Okay. So this dipolar model of dark matter was introduced earlier, and from the experiments now, one has been able to put some bounds, that so far from the electron scattering, one put some bounds on the dark matter So if you don't observe some signal from some up to some time, you can put some bound. So this is this blue, dark blue is this xenon 1 ton, and there's another experiment dark side. So there is some anapole moment versus mass exclusion region. The region above these shaded lines are ruled out for the anapole moment, dipole moment, and electric dipole moment of the dark matter. But so just one technical slide. So I just showed that if you have dark matter which has this electromagnetic form factors, what will be the scattering? Actually, one can classify all operators which are interaction of any kind of dark matter with electrons with the unknown coefficient. The coefficient will depend upon the coupling constant will depend. For instance, the charge, the dipole moment or the electric anapole moment will come from the new physics, but the form of the operators can be figured out from the fact that the dark matter can be a scalar spin 0, in which case you will have this operator. So the operator will be just the charge of the dipole times the charge of the electron, or so the density of the dipole times the density of the dark matter times the density of the electron. So the Hamiltonian will be just the identity matrix with some coupling. Similarly, it could have the spin of the electron could couple to this velocity of the dark matter. The spin of the electron could couple to the spin of the dark matter, and so on. Okay. So there are just these operators which are there, and this O17 to O20 is if the dark matter is of spin 1 object, not spin half object. So you can have some more operators. So independent of what the basic physics is, as far as the atomic physics goes, one has to take one of these operators and then work out what is the transition rate for a particular atom or a particular the transition rate between two levels or ionization rate for a particular atom which is being looked at in the experiment, for instance, xenon or argon, and then compare with the experiment, and that experiment will give you that coupling like the dipole moment or the anapole moment. So atomic physics only takes these operators and works out the rates, and from those rates one gets the coefficient when comparing with the experiment. So there is a lot of experiments or theoretical effort which goes into this calculation of this dark matter transitions from atoms, and by comparing your theory with the experiment, one gives you this, one gets the exclusion plots. And as I said, more than exclusion plots, we now have inclusion plots, and now we have a signal. So this is the signal which is seen, but actually interestingly, this energy, this low energy of the signal, this is less than 5 keV, is not coming out from, I mean, there are many models. This result has spawned many papers, but the leading candidates for this event is actually, interestingly, not dark matter, but the following. So actually the leading candidate is that there is excess tritium. Okay, there is a tritium which decays, and that can give you this excess electron. So there is more tritium than they think, although the experiment is sure that they have figured out how much tritium there is. But so this dashed line is what is the experimental expectation of the tritium signal, and this is what is seen. So there is, if there is a big discrepancy of your tritium estimation in the xenon, then you will see this kind of signal. So this is a conventional explanation. More exotic explanations are, there are particles from the sun, axions. Okay, they are emitted from the sun. They come and then they scatter the electrons in the xenon, and so this axion scattering from the solar solar axions scatter the xenon tank, and they give you this signal. The other is, if you have the solar neutrinos by this flux, neutrino energy versus this flux, okay, So it is well known that the sun emits neutrinos, which have been well measured. Now, if those neutrinos have a magnetic moment of something like 10 to the minus 11 Bohr magnetrons, then through that magnetic form factor of these neutrinos, you can have this signal. So most observers believe, and that right now it would be good to wait for better statistics to see if these error bars go down. And so this is right now something like a 2 sigma signal. And in particle physics, one considers it a discovery or a new signal if it's a 5 sigma signal. So one has to wait for better statistics to see whether you can, whether this is a genuine signal or this is a background. But there is something interesting going on even from experiments, which has spawned a lot of publications in this field. So all these calculations involve transitions of this from this xenon, and those are atoms, and those are very complex calculations in atomic physics. And one has to do those things. So as I said, that this exotic physics reduces to one of the operators that I listed. And once that operator is there, you work with the atomic physics calculation of what transitions, what is the rate of the transition, and so on. So this is the theory and the experimental effort which is going on right now. And right now, the effort in detecting this MeV scale dark matter is through this electron transition in heavy atoms. Okay. So atoms are a good testing ground for fundamental physics. And a good review paper on this is this one. So this has details of what the atomic response, or the calculation of what calculations you need to do to compare theory with experiment. So I think I've, and this is the end of my talk. So thank you, and I can take questions.
Many thanks, Professor Mahanti. The session is open for discussion, and I have 2 queries, or even a third. So let me read them for Professor Mahanti. There is a query from Koel Day, and the question is, can we say dark matter is in atomic or molecular state, or do we have to assume that too? That is, we have to actually assume the state of it in the atomic or molecular state. That's the question.
Okay, so the dark matter nothing is known about the dark matter, so it is possible. So the only thing that is known is that it has, the charge is 0 or it is extremely small, whereas it can have dipole moment. So for instance, it could be like a neutron which has 0 charge, but it has a dipole moment. Also, the dark matter may be an elementary particle like an electron or a neutrino, but it also could be a composite particle. For instance, you could have a proton and electron on the dark sector which do not have electric charge that interacts with photons. So then you can have a dark atom. So there are many possibilities, and right now that possibility also exists, that dark matter can be a composite like an atom.
Many thanks, Professor Mahanti. There is a second question, and that's from Srinivas Prasanna. Is there any special reason to choose noble gas atoms as candidates for these experiments? Have there been other atomic candidates that have been proposed?
Yeah, that's the first question one should ask. That why go through the trouble of looking for this? Collecting the noble atoms. So the first thing is you need atoms which have a large number of electrons, because that's what the number of target electrons increases when you have a big atoms. The noble atoms have this, the electrons are tightly bound. So the possibility of scattering electrons from by background radiation is smaller when you have these noble atoms. So to minimize the background transitions, the scattering from the background, that you need to have the electron tightly bound to the atom, you choose this noble gases or the noble elements. So you need noble elements which have heavy mass. So xenon is one of the good candidates.
Thanks, Professor Manti. There is a second question from answers to other questions, and if there is time, then we can come back to Prasanna's other questions. So there is a question by Anmol Subba, and the question is, WIMPs are hypothetical particles. Then how are we considering its mass to be 100 GeV?
Yes, so we have no idea about the mass of these particles. So this 100 GeV was something which was actually coming from theory. Supersymmetry is a theory which is an extension of the standard model. And in supersymmetry, one predicted particles which will be of 100 GeV mass. And there was expected to have particles which have 100 GeV and zero charge, like neutrinos. So that was a theoretical sort of prejudice. But now we know that the cross section of those particles is very small. I mean, the observed cross section, I mean, there is no scattering seen. So then the next target is that you have to think of maybe the dark matter is of lower mass. So the 100 GeV was a theoretical prejudice, which is where the first place to look for. Also, the experimentally, since the nuclei were 100 GeV and the dark matter of 100 GeV would be the most sensitive, most efficient transfer of energy. So from the experimental and theoretical side, 100 GeV was the first target. But right now, nothing is known. So we are looking at now people are looking at lower mass dark matter, like MeV dark matter.
Many thanks. There is another question. Other than the rotation curve, are there any other evidences for dark matter?
Yeah, I showed very briefly the first slide. So actually the dark matter is needed in cosmology for structure formation. So it is known from in the standard cosmology, unless you have a dark matter background, okay, the fluctuations in the dark matter cause potential wells, and then the baryons or the normal matter falls into those potential wells, and that creates galaxy. So from a smooth universe, if you want to create galaxies, you first need a fluctuation in the dark matter. So that is actually the biggest reason the dark matter is needed in cosmology to form structures. Now at the galactic scales, we have these rotation curves which tell us that there must be dark matter. And from the rotation curve of Milky Way, we know that this dark matter mass density must be 0.4 GeV per centimeter cube.
Thanks, Professor Manti. There is another question, and this now we take because we have time. So this is a question again from Prasanna, a naive question. Is the d sigma over dE expression is f square evaluated at q square equals 0, the form factor of the dark matter particle?
No, it's a function of the momentum transferred. So this is a this f are also functions of q. Fp and Fn that I have put there, those are also functions of q. So those are not evaluated at zero momentum. They are actually evaluated the momentum at which the energy transfer takes place, which are of a kV magnitude.
Thanks a lot. And there is a question from Nataraj Hulia. Do neutrinos have non-zero or relic electric charge? You mentioned about them having magnetic moment.
So Neutrinos do not have an electric charge. So standard model does not allow the neutrinos to have an electric charge. And however, neutrinos may have a magnetic moment, which are generated through radiative corrections, so quantum corrections. So they do not have a classical magnetic moment, like the electron has a classical magnetic moment, but the electron also has an anomalous magnetic moment, which are induced by QED. So the neutrinos may have also, they have zero classical magnetic moment because they have zero charge, but they have anomalous magnetic moment, which are induced by quantum corrections. So those, if they have those, the anomalous magnetic moment, that could be one of the things that is seen in this xenon signal.
Many thanks. There is a question by Vineet Kumar. What are the intrinsic properties of dark matter, like spin, charge, or something like that?
Yeah, so what you need for dark matter, I mean, to predict what the dark matter is going to do in the experiment is, first of all, what is the spin of the dark matter? So you can have a spin 0 dark matter, spin 1, or spin half dark matter. You should also know from the theory, or at least your model, that the dark matter, how it interacts with the standard particles, so that it can emit one of the known particles. For instance, it can interact through a photon, a W, Z, or a Higgs boson with the known particles. It can also interact with our known particles through a still unknown particle. So you can have a dark matter, also a dark mediator. That possibility also exists. So right now nothing is known. So there are models for everything. So once an experiment sees a signal, people start then testing these models. So right now there are many possibilities.
There is a second question by Vineet Kumar, but there is a fresh question, and this is from Ashok Kumar Pati. This is vis-a-vis your statement on dark atoms. If there is no charge for the proton or electron, how will you form atoms?
No, when I said no charge, that means, see, there is a theory called the mirror universe. So what is said is that the standard model is actually has a left-handed symmetry. I mean, it's SU2L. So what is said is there is also an SU2R. There is a mirror image of the standard model, and that mirror image of the standard model interacts with us gravitationally only. It does not interact through any other any other particles. So you can have an image, mirror image of a proton. Mirror image means a partner of a proton and a partner of an electron, which have their own kind of charge. So it's a different charge. So they have a charge in that universe, but that charge is not the one which interacts with our charge. So it's a different charge. The charge of that universe is what binds the atom together. But that charge is not the charge, our electron charge. So it does not interact with our universe except through gravitational.
Let us take this second question by Vineet Kumar. We have some time. Is there any way geometrically to distinguish between the dark matter and atom? Also, is the dark matter representative of quantum fluctuations?
Okay, so the first thing, this thing is that one way in which you can tell that the dark matter is an atom instead of an elementary particle is that if you can cause a transition of a dark matter from the lower state to the upper state, and then that there is a transition back, and that back transition imparts some energy to your target. So for instance, dark matter which is flowing through one target gets excited to the higher state, and then that higher state imparts some energy to another part of the target. So from these transitions, if you can get energy out of the dark matter, that means there is some internal transitions taking place. So one looks for this inelastic scattering from this dark matter as a sign that it is a composite particle, not an elementary particle.
So we have no more questions, and let's all thank Professor Mahanti for a very stimulating talk, as is also evidenced by the volley of questions. And also thanks for strictly keeping to the time, Professor Mahanti.
Thank you very much.
Many thanks
Thank
for
you.
that stimulating talk.
Thank you. Bye-bye.
So we go over now to the next speaker. So,
okay.
Right. The next speaker is Professor Koichiro Asahi of Riken, Japan. And he's going to talk about electric dipole moment of diamagnetic atom 120 xenon as a probe for new physics.
Professor Mukherjee, we have another speaker we have replaced. So he is in the 4th position, and the 4th speaker will be the 2nd one.
Oh, I see. Okay. I remember Professor Schmidt-Wellenbuch telling something else. Okay. So, there is a change of speakers, and Dr. Philip Schmidt-Wellenbuch would be the 2nd speaker, and he's going to talk on the new limit of the neutron electric dipole moment. And if Professor Philip Schmidt-Wellenbuch has joined just recently, in the 30-minute slot, 25 minutes is for talk and 5 minutes for discussion. So,
thank you very much.
Professor Schmidt-Wellenbuch is from Paul Scherrer Institute of Switzerland. So, Professor Schmidt-Wellenbuch.
Thank you very much for this kind invitation and the introduction. And I would like to wish Professor Das a happy birthday, to his 65th birthday. Congratulations. Today I will talk about the latest episode in the quest for an electric dipole moment of the neutron, which took part at the Paul Scherrer Institute in Switzerland. My talk is about the experiment itself, you see here, then about the measurement, and finally the publication. Let's move on. So this story started already in the 1950s, long time ago, on this thermal reactor here at Oak Ridge, number 17, Ramsey and Smith measured the first time a neutron EDM. The reactor was actually used originally for breeding plutonium during the wartime, but then after the war, it was immediately used for fundamental research, and that's a nice sign how ARM research can also help fundamental physics. It's a long time since then. Many measurements have been done. This is an overview of all the EDM measurements which have been done since. This one is the first published in 1957. Actually, the measurement itself was done already in 1950, but Smith, Purcell, and Ramsey didn't actually publish it immediately because they thought it's too daring to put into question symmetries. But then there was the publication of parity symmetry violation in 1957, and as a consequence, they also published their research. Since then, violations of symmetry is kind of textbook physics, and many people have searched in all these different molecules, atoms, and nuclei for CP violation via a neutron or via an EDM. So the leading or the smallest value is by mercury EDM. Cerium oxide is citing here a value for the electron EDM. This is xenon EDM. You will hear a talk about that later. The neutron EDM, a new point has arrived. I will talk about the new point. These are deduced electric dipole moments from the proton, and up here is the muon. Just to give you the scale of what we are looking for. So this is measured in electron centimeters. So the displacement of a positive and a negative charge in centimeter. So it's nearly a classical unity. And you can see that the neutron is about 6 orders of magnitude above the background from standard model, which is the CKM CP violating phase. Then you have the electron EDM, which is still nearly 9 orders of magnitude away from the current best from the standard model, and the mercury, which is also 6 orders of magnitude. So there's a huge distance to standard model physics, and this huge space here could be having signs of physics beyond the standard model, and is extremely interesting in the today's particle physics environment, as there are only little signs of some violation somewhere, but not a real lamppost which tells you here you have to search. Now, going back to the reason why it's so interesting to measure an electric dipole moment, and that's the intimate relation between an electric dipole moment and violation of the combined symmetry of charge and parity. What you see here is a level splitting, like a Zeeman level splitting of a particle with a magnetic moment and the spin half, and you see the larger the magnetic field, the splitting increases, and just in the same way, an electric dipole moment would lead to an energy splitting of the spin in an electric field. But then, if you now concentrate on the spin up state and you would perform a T reversal symmetry, you see that the magnetic moment stays in the same state, but the electric dipole moment would flip states. So it would have suddenly a negative energy eigenvalue. And that's extremely extraordinary, because that's indicating T violation. And assuming T violation, also CP violation. CP violation is so fascinating because it's a missing ingredient in the baryon asymmetry of the universe. It means that there is much more matter than antimatter as we anticipate. It arises in all sorts of natural models beyond the standard model as a natural ingredient, and so it's always there. And there's even in the standard models something which hasn't been discovered yet, and that's from the strong CP violation in the theta term of the QCD. And whenever there is a CP violation in physics, there would be an electric dipole moment if it's in a fundamental particle with spin. You might have wondered why there are so many different systems worked on, and why it's so interesting to measure not only one, which is the best electric dipole moment search, but many different, like the proton, neutron, like these weird and fascinating molecules, thorium oxide, hafnium fluoride, or paramagnetic atoms and diamagnetic atoms. The reason is that each of them has a long path from the energy scale where the experiment actually takes part, which is at the electron volt scale, up to these fundamental theories which are CP violating beyond the standard model. And each of these paths is slightly different. And so to disentangle what physics exactly would lead to CP violation, a combination of all these paths would enlighten you much more than if you only follow one path, and then you can't distinguish whether the EDM of the neutron is, for example, a QCD term, or whether it's quark or gluon EDM or something even more fundamental. So how do you measure that beast? The beast is measured by measuring the energy splitting, as you have learned also in atomic physics. The easiest way to measure the energy splitting in a spin 1/2 system is to measure the Larmor frequency of this system. So we call that a Larmor frequency of the electric dipole moment. Now, if you use the values for the neutron EDM, it's about 1 × 10⁻26, the electron dipole moment, you can go to fields of about 20 kilovolts per centimeter, and you look at the frequency, that's a really small frequency. It's 36 nanohertz, which is about 1 turn in a year. At the same time, in the best places where you can measure such thing, you will try to shield your magnetic field from the Earth, and you can have magnetic fields which are smaller than nanotesla. But still, this would lead to a millihertz frequency from the Larmor frequency, and that means a turn in 15 minutes. And so you can't measure that independently of the magnetic field. You have to really take the magnetic field always into account. And for that reason, you actually take a strong magnetic field. Well, strong is relative. It's a 1 microtesla field you take. And then you add once electric positive field, then you have an increase or a decrease, in this case, an increase in the frequency. And then you take once a negative electric field. You take the difference of these two measurements relative to a very well-known magnetic field. Then the magnetic field is canceled because you know it's so good. And what is left is the electric dipole moment of your system, in our case, the neutron. How do you measure such a frequency? A classical measurement of frequencies is Ramsey's technique of separated oscillating field. I will explain you that briefly here. You start with a spin-up system. You, so to say, polarize all your neutrons. Then you apply a spin 1/2 flip. The spin 1/2 flip tilts the spin into the perpendicular plane, in the same plane as the oscillating magnetic pulse has been applied. It is chosen such that it's perfect in the center. Then you let precess for a long time T, here T, the Larmor precession of the neutron in the static magnetic field, and then you apply a second oscillating field. Now, if you vary this oscillating field, like this, here that's what is the frequency in a 1 microtesla field, then you get a Ramsey envelope and a Ramsey oscillation interference pattern. You see that here, that's how this interference pattern looks, and the resonance frequency is the most central fringe. And that's what you try to measure. And the sensitivity is 1/alpha, which is the visibility of this fringe. So you want to have 1 at best. T is the length of the time you let freely precess your neutrons, and square root n is the number of observations, so the number of neutrons. To measure an electric field, you add an electric field positive and negative. And what you actually do is you measure only at the central 4 steepest slope points. So you get 2 measurements, one of the with a magnetic field, electric field positive, one with an electric field negative. Then you fit here the central fringe, you get 2 frequencies. The difference of the 2 frequencies is canceled, the B field, and you get again the electric field and the electric dipole moment dependency. And so this down here is the figure of merit. So you also need a very high electric field to get the most out of your measurement. That's what we try at Paul Scherrer Institute using ultra-cold neutrons. Ultra-cold neutrons are neutrons which are extremely slow and frozen. So they have a millikelvin temperature approximately. They move with about 8 meters per second, and they are confined in materials with energies up to 300 nanoelectron volts. So this characteristic feature that they can be reflected under all incident angles is coming from the strong force, which is here the scattering length of the neutron on the material. So what we have a strong neutron beam, proton beam coming in. We have spallation. We have energies of more than 200 mega electron volt, which are cooled down thermally in a moderator with D2O. Then some neutrons come into a crystal made of solid deuterium. Here they can excite phonons, and then they lose their energy by giving the energy to the crystal, which is cooled away. And the rest energy of some 100 nanoelectron volt leads that the neutrons are bouncing inside these guides to our bottle, where we close the door for the measurement. That's the filling period. Then we have a lot of neutrons inside this bottle. That's the electric field, which is applied from the top. The ground electrode is on ground, obviously. Then we store for 180 seconds. Then we open the shutter, and we empty, and we detect in 2 different detectors, spin up and spin down, and take the asymmetry of that. And that gives us one single measurement with about 15,000 ultra-cold neutrons. The sensitivity, as I showed you, goes with square root n, e, and t. And in 2013, when we started operation, we were measuring with a sensitivity per single shot of about 2 × 10⁻²⁴. And then since 2015, when we have optimized the entire apparatus, here are the numbers which are relevant for this equation. We have about 20,000 neutrons. We can store them for 180 seconds. The field is relatively high of 11 kilovolt. Asymmetry is 85%. And we have a decoherence time of more than 1,300 seconds. And that led then to a clear increase by a factor √2 about, and that was used then to accumulate over 2 years data. Another thing which is extremely important in that respect is that one needs a very stable magnetic field. Otherwise, these 4 points will not lie on the route, on the fringe, but somewhere else, and then you get a big bad fit and you don't profit from your initial sensitivity. For that purpose, we have different features. We have an active magnetic shield, which is a coil cage, which reacts to changes in the environment. We have something which is a magnetic shield outside, and inside we have a mercury lamp and polarizing cell, which mercury is polarized, and we look at the precession signal inside the same chamber inside here of mercury atoms in the same magnetic field. So first we polarize the mercury, then we inject it into the same chamber where the neutrons are, we spin flip them again, and then we observe a free precession signal, which you see here. That's the envelope, that's the precession signal. This is real data, which has about a decoherence time of 140 seconds. It gives us a sensitivity of some 100 femtotesla. And that is used then to normalize the real data from the neutrons. Here you see the neutron alone in a typical cycle run. These are some 100 cycles, which are with electric field changes, so positive, negative, positive. And then you could say, well, here it changed with the electric field, but then you see again, here the mercury is showing you the same. And if you take the normalized value, it drops out, and you can actually measure for a long time and accumulate data over a long time with your sensitivity. However, such a normalization has also a backdraw, because there are systematic effects which come into this ratio of the mercury neutron frequency to the mercury frequency. First, there are the electric dipole moments of neutron and the mercury, and the neutron is the one we are looking for. The mercury EDM is so small that it doesn't matter. Then there's our dominant systematic effect, which is the V cross E effect, and this, which is also sometimes called geometric phase effect, and or ordered motion. Another one, which is negligible, is that we have a quadratic effect, and all these back here, they are not dependent on the electric field, and if everything stays the same, R plus minus R minus, these will drop out. So what we actually do is we have this geometric phase effect, which is an effect of the magnetic field due to the V cross E effect, which is depicted here in the red, and the gradient field of the magnetic field non-uniformity. And these two together, their multiplication actually leads to a phase shift in the frequency and to an electric dipole moment sort of signal. That sort of signal is so large for our chamber with 47 centimeter diameter that if you go through the calculations, you would get something like 4 times 10 to the minus 27 E centimeters per picotesla per centimeter. So you have to really control the uniformity of your magnetic field in the range of sub-picotesla per centimeter gradients. We do that by exploiting a second feature of our experiment. That's quite funny. So the ultra-cold neutrons are heavy, and they are affected strongly by the gravity. And that's why they are sagged to the bottom, and the different typical displacement is minus 0.4 centimeters. So the center of mass of the ultra-cold neutrons are 0.4 centimeter below the center of the mercury. And that little difference leads to this change in R's. So this R minus 1 actually gives you a displacement, a measure of the gradient. And then we can do that. We measure here the electric dipole moment as a function of the gradient. So we deliberately change the magnetic gradient regularly in our chamber and measure the EDM as a function of the gradient. And then if we go to zero gradient, we really measure the real electric dipole moment. That was how the measurement worked. We in totally took 99 sequences, each sequence about 500 cycles. So we had something like 555,000 cycles. And in average, we had 11,000 neutrons per cycle. This led to a statistical sensitivity of 1.1 times 10 to the minus 26. The next thing was checking all systematic effects. And I will look at these. I told you the problem with the fails EDM already, with the V cross E effect and the gradient, and that was resolved higher orders with the field mapping. So every time when we do this correction, we don't actually have here only G10, but instead we have all uneven multipoles of the magnetic field kicking in at some other level. The same is true not only for the measurement of this gradient, but also for the measurement or the effect of this fails EDM. So this is also not only G10 as over here, but also a combination of all higher order magnetic field multipoles, but slightly different. And so one can take the difference of these two, and one needs to know G30 and all higher order terms. And for that purpose, we use a magnetic field mapper. Here's a little magnetic sensor, a flux gate. It moves through the entire chamber in different planes, so in total 5 planes, different radii, and it measures the magnetic field at each individual point. And from that, you can deduce the higher order multipoles of your field and subtract them from your magnetic field readings with your R value. And what you get then is an EDM. Here's the corrected EDM as a function of the gradient. Down here, again, this is this R corrected, which is the measurement of the linear gradient. And then you see this linear behavior. And the crossing point of these two, so that's for B0 up, that's for B0 down, that's when the main magnetic field is pointing upwards or downwards relative to gravity. Well, you measure this as a function of gravity because you measure it by R, and the crossing point is then your electric dipole moment. And now you might be astonished that we have measured an electric dipole moment, but this is due that we have blinded all data. We had two analysis groups who had two different sets of blinded data. Then we compensated for drifts of this gradient by using a relative measurement with cesium magnetometers, and there was a non-anticipated systematic effect we controlled sufficiently well, which is the incoherent scattering of the mercury atoms inside our chamber. In total, we came to a systematic of 0.2, which is a five-fold improvement relative to the previous measurement. And then we had to unblind the data because we had double-blinded data sets. This double-blinded data set of the two different analysis groups were giving the same statistical error, so we decided to unblind relative to each other. This was the result you have seen just recently, also in the plot. So there we also agreed relatively good, and that's why we then said, let's go, and we unblind fully, and when we fully unblinded, the central value was combined data at 0. So our final result was 0 plus minus 1.1 plus minus 0.2, 10 times 10 to the minus 26 electron centimeter, which also results in the best current upper limit of the neutron EDM, which is just below the latest best upper limit. In the future, we intend to measure that another factor 10 better. We are currently setting up the experiment at Paul Scherrer Institute and hope for start of the measurement coming years. At that point, I would like to thank everybody in the collaboration who made this result possible, and the audience for the patience. Are there any questions? Thank you very much.
Many thanks, Dr. Schmidt-Wellenburg. The talk is open for discussion, but I don't see any queries put up on the chat note yet. Okay, so now I see again from Srinivas Prasanna. May I request you to elaborate on the need for a magnetic field a bit more?
Yes, indeed, I will do that. Just a second, I try to see if I have a slide for that. A moment. So the essential idea why it needs a much better understanding of the magnetic field is that, here you see that, maybe, yes. So essentially what you have is that you have this a magnetic field dependent systematic effect. And as I told you before, it's essentially a function of G10, which is this gravitational linear gradient, we call that. That's a combination of, if you integrate over the central volume of the chamber, of all uneven multipoles of the field integrated over this volume. This is, so to say, this crossing point GG. And then something is left. If you do that, then there are other parts which comes only into this equation for the phase EDM, which also depends on higher multipoles. So you could evolve that to much higher order, but they get much smaller. So much smaller than it actually continues. So we did it up to G70, and G70 was negligible. And then you have the dependence of these uneven multipoles which you have to correct for each electric dipole moment measurement at a different gradient setting. And these gradients here you get from a multipole expansion. So sorry, I will try to find the correct slide again, which we used previously. Here, so what we can do here is that as you have at each of these points, you have a vector information of the magnetic field in the entire chamber. You can fit spherical polynomials which obey the Maxwell equation to these points. It's a field expansion. And so you get, as zero order, you get the main magnetic field, which is 1 microtesla. Then you get 5 linear gradients, for example, which is the vertical, the 2 transversals, and then something like dBz by dBx. And then you can go to the next order, to quadratic, then you can do cubic, and so on. And we do this expansion with these field measurements. And so we can expand the full field into its multipoles and use these multipoles finally then for the correction of these nasty higher order terms, which you see here again, these combinations of higher order. Did that help you? Thank you.
Okay. There is another question, and this is from Anmol Subba. Can you explain a bit more how is EDM violating CPT comes? Maybe it is a bit short. It just essentially wants you to explain a bit more about how
Yes.
EDM
So
CPT
an electric dipole moment is coupling the spin of the particle to the electric field. And now if you look at the spin, which is a axial vector, and the electric field, which is a normal vector, and you apply a parity transformation to that, then you will see that the electric field will flip over, but the spin will not. So you have first you have 2 spin up states, and later you have a spin, or two spin vectors which are 1, so to say, and later you have 1 and -1. And so you change the eigenvalue of the Hamiltonian. So what I have shown you there is essentially the Hamiltonian of the spin coupling to the electric field. And this Hamiltonian, if it changes the eigenvalue under a transformation, then it says that it doesn't obey this symmetry transformation because it violates the Hamiltonian. That's a fundamental statement valid for all physics, essentially. And this is exactly the case. And the reason for that is, as I said, that the electric field and the spin are not both the same sort of vectors. One is an axial vector, the other a normal vector. Whereas, for example, in the magnetic field coupling to the spin, you have 2 axial vectors. And so they transform in the same way. And so they conserve all symmetry transformations. And the Hamiltonian always stays the same, and the eigenvalues of the Hamiltonian too. Did that help a little?
Many thanks. There are no more questions, but we still have a time of about 3 minutes or so. So I'm waiting for some other. Okay, now there is a question from, okay, there are 2 more. I don't know how much we can do that. Okay, so there is a question from Minori Abe. I'm sorry if I missed your explanation, but is there an estimated range for, I don't know what is dN?
The electric dipole moment.
Oh, electric dipole moment, yeah, from particle physics models. Is it close to the current upper limit you obtained?
Well, for example, in SUSY, if you would use natural phases, so orders of the CP violating phases similar to the one in the CKM, the natural range would be 10 to the minus 25 or so, and we are already very stringently ruling out SUSY, all supersymmetric models, and one could say that you have to fine-tune all supersymmetric models. So what people now discuss are double Higgs models, or models which have a lepto-quark models and things like that. And there it is always such that these models which came up now and which are popular, obviously integrate or have as a benchmark that they have to be in accordance with the current limit. So there, when it says that in the next order of magnitude, one can make a large step forward. However, there are so many models and so many fine-tuned assumptions that one always can fine-tune these models again. So one thing which is very different in that respect is the theta term of the QCD, which is limited essentially only by the neutron EDM or by the model dependent by the mercury EDM. And essentially the measurement itself gives the limit on this parameter in the standard model. And there one would actually expect that the value of the theta phase of this QCD Lagrangian should be order 1, but instead it's 10 to the minus 10. And so this is a big question, and people came up due to that with something which is called the axion and the axion field in the early universe, which leads again to dark matter. So in one respect, one sort of dark matter candidate particle is the creation of this CP, strong CP problem in the neutron EDM measurements.
Many thanks. There are two questions, but we would take one, the one from Vijaya Sahu. There is a second one, which is from Koel Day, probably. But that I would request Ms. Day to write to the speaker directly. So I'm really reading out the question from Vijaya Sahu. The limit obtained from direct EDM measurement of neutron, and that is obtained from mercury EDM measurement, seem to agree. That looks quite nice, but the limit obtained from mercury EDM has large uncertainties from nuclear calculations. Do you think this agreement is just a coincidence?
As it only a coincidence, yes, I think it's a coincidence. As it's only a limit, I think it's a coincidence, yes. So you're right, the calculation of the neutron EDM from the mercury measurement has a single source assumption, which is, for example, if you would have the theta term, would be quite weird because the proton EDM should then also have a value as the neutron EDM too. But even going beyond that, the matrix elements in effective field theories for many of the things which happen actually in the nuclear are not fixed. So they have big error bars too. So the entire thing is a coincidence. And it would be different if we both would have measured an EDM and then the neutron EDM would coincide. Then I wouldn't think it's a coincidence. But at the moment, I do think so, yes.
Many thanks. So we take no further questions, and let's all thank Dr. Schmidt-Wellenburg for an excellent presentation. And the first part of the pre-lunch session is over now. We take a break for half an hour. And in this half an hour, you can have essentially a look for the poster presentation. And how to find that, I think some of the moderators might be helping you.
Yes. So Professor Mukherjee, I have typed the access to all the poster presentations in the chat window of Zoom.
Okay.
So I hope you all enjoy these posters during this short break. I especially request everyone to give likes to posters which they think they are deserving, because this is going to help us grade them. And also you can ask your questions by directly going to the YouTube link for that poster, which is provided on the website itself. So you can ask questions, and all the poster participants have been requested to remain active on their respective videos so that they can answer your questions. The same link has been shared in the YouTube comment box as well for the audiences who are with us on YouTube. Thank you so much.
Many thanks, Vindhya. So we take a recess for half an hour and we assemble again at 12 o'clock exactly for the second part of the pre-lunch session. So we take a break for half an hour and I also go off the air.
Hello.
So we have a minute left, so let's wait for that. Okay, we are ready to begin. So, welcome back, everybody, to the meeting after the poster presentation break. The speaker of this session, at least the first speaker of this session, is Professor Takatoshi Aoki of the Institute of Physics at the Graduate School of Arts and Sciences, University of Tokyo, Japan. So I'm inviting Professor Aoki to take the talk.
Okay. Okay. Can you see this slide? Okay. I share the slides. So can you see?
Right. Yes, we can see.
Okay. Thank you. So first, I appreciate Professor Kafu and all organizers to have an opportunity to give a talk here today. And happy birthday for Professor Das-san. Today, I talk about the electron idioms R. No.
Dr. Aoki, can you
Okay.
actually, can you increase the volume of your speaker somehow?
Pardon?
The volume of the volume of your voice is somewhat low. It's audible, but maybe a bit could have been a bit better. Please go ahead anyway.
Okay. Can you hear?
Yes, we can hear.
Okay.
A bit low. That's
okay. First, this is outline my talk. So, first I talk about the nuclear spin independent parity integration to prove nuclear beyond the standard. This is the topic in the transitional teaching. Next is the nuclear spin dependent term to study nuclear anapole moment in the transfer. But finally, we briefly introduce our explain the current situation. But my main talk is 1 and 2. First, this is the introduction. Okay. So this is weak interaction in atomic systems. So study of atomic parity non-conservation effect have the potential to probe the nucleus beyond the standard model. But okay, this figure means Coulomb interaction inside the atom. So this atom consists of the electron and the nucleus. But so there are mainly two sources in the weak interaction in atomic system. One is the nuclear current weak interaction by exchange of the G boson between the electron and the nucleon. Other is due to the nuclear anapole moment. First, I talk about this nuclear current weak interaction. So for understanding this weak interaction, first we consider the equation of continuity in quantum mechanics. So this is the probability density of the wave function, and this is the expected value of the velocity. So so-called current in non-relativistic form. But in relativistic form, this current is written by this equation. So this includes a Dirac matrix. So in QED, the Lagrangian of this Coulomb interaction between two electrons given by this equation. So this Lagrangian is a product of the two current of the wave functions. Similarly, Wink interaction is also given by a similar equation. This current is a current of the neutron to proton. Other current is electron and neutrino. So, but to violate parity, this Lagrangian should include the term of the gamma 5. This gamma 5 is very important. So first we consider this gamma 5 included in the only the electron current. Then we have to consider the all weak interaction inside the atoms for each quarks and each nucleons in the nucleus. After summation of this Lagrangian over all the nucleus in nucleus, we obtain the this Hamiltonian. So this QW is so-called weak charge. So this G is a proton number and N is a neutron number. So this Hamiltonian does not include the nuclear spin component. Therefore, it's so-called nuclear spin independent PNC effect. So in then, okay, we consider the new physics. Now we assume the new particle G prime boson between the electron and the nucleon with mass lambda. If this particle have a similar interaction, then if we observe this weak charge, we cannot distinguish these two Lagrangians. Therefore, observed QW is shifted due to the new physics. There are several scenarios changing the QW. First, extra G boson in SO10 due to the grand unified theory. Professor Marciano calculates this mass scale with this mass of the new particle. So using this equation, we calculate the effect of obtained mass using this QW due to the cesium experiment. Then this predicts 900 giga electron volt. And using this, now we consider francium atoms. This gives more than 1 tera electron volt. So other scenario is R parity violating Suji. So now Professor Ramsey Muzdorf considers the electron quark interactions. Then this equation predicts the mass of more than 5 tera electron volt for francium atoms. And also dark matter is also predicted by the Professor Marciano. He suggested as a dark parity violation. So Higgs particle might decay to the G boson and the dark G boson. So this dark G boson is useful to explain the muon G-2 factor anomaly. This is the mass of G boson, and this is the coupling of this particle. This shaded area is already excluded by the muon experiment, and the atomic parity violation experiment in cesium also excluded over this area. So this if we overcome this area, we can exclude the other new area using a Francium atoms. So this is history of the parity violation. So there are many experiments. The most accurate experiment is given by the cesium experiment in 1997. And recently, yttrium atom is also gives a new value for the weak interaction for the each isotope of the yttrium atoms. They observe the isotropic variation of the weak interaction for atoms last year. So we propose a new experiment using francium atoms. Francium atoms have the weak charge QW of the minus 155. To observe this effect, we consider the atomic transition in the francium. So we consider this transition between the S and D state, the D3 half state. This transition is the E2 transition, but this is also included the E1 PNC transitions. So Professor Safu and Das calculated the calculated the matrix element of the E2 and the PNC transition for the many transitions. Then finally, they obtained the new matrix element for francium atoms. So in experiment, we would like to measure this matrix element. So we consider the light shift due to the interference between the E1 and E2 transition. This is originally proposed by the Professor Hodgson. Sorry. So we consider the Rabi frequency for the E1 PNC transitions and E2 transitions. This E1 means dipole moment, transition dipole moment for the E1 transition induced by the PNC effect. And this is a matrix element due to the E2 transition. So effect Rabi frequency is given by the summation of these Rabi frequency. Then if we measure the light shift, in other words, AC static shift in this hyperfine state, we can obtain the QW. This measurement is also calculated for barium ion and radium ion by the Professor Safu and Professor Manas Mukherjee. And I appreciate Professor Mukherjee. So using these equations, we calculated each light shift in the hyperfine level in francium atoms. Then we we found the same E2 light shift for the MF equal 7.5 and 9.5. So we think these two sub-levels might useful to cancel the Zeeman effect. This is the experiment procedure. First, we laser cool the francium atoms with a laser beam with a wavelength of 718 nanometer. And for state preparation, we apply this optical pumping beam, and we apply this laser beam of the 16 nanometer beam to create light shift. We applied RF field and microwave field for state preparation. This is the optical pumping scheme. We apply the laser beam to create the spin polarized atoms in this state. After that, we apply the two laser beam for stimulated Raman adiabatic passage to create this 7.5 state and 1.5 state. Okay, this is selection. And finally, we consider these four states. This is the m equal 1/2 and minus 1/2 state, and 9/2 and 7/2 state. We measure these two transitions. So after subtraction, we obtain the 7,000 millihertz of the PNC effect. This is the magnetic field, and this is the light shift. If we as changing the magnetic field, we can obtain this graph, and this offset means the PNC induced light shift. So if we observe the shifted QW, this axis means the shifted value from the value predicted by the standard model. If we measure the 10 millihertz, this means the new particle with the mass of the 6.5 tera-electron volt. This is our new result, and we also suggest this scheme for ultra-cold cesium atoms in optical lattice. So Professor Kastberg developed a method for the optical lattice scheme. We consider this PNC transition and this lattice transition. This is a experiment diagram for two-dimensional optical lattice. So we consider the E2 light beam with a wavelength of the 689 nanometer. And this wavelength for optical lattice should have this wavelength multiplied by √2. Then this localization point of the standing wave for optical lattice overlaps this antinode in the standing waves of the E2 transitions, E2 laser beams. Therefore, all atoms can feel the E2 light beams and gradient of the E2 light beam. So after the considering cancellation of the E2 light shift and first order Zeeman shift, we obtained the PNC light shift of the 0.9 Hz. So for this result, Professor Safu and Das calculated the E2 and PNC matrix element for cesium atoms. Using these values, we calculated the light shift for cesium atoms. PNC effect have these values. Then we obtain the 0.9 Hz for our measurement scheme. So if we measure the QW with an uncertainty less than 0.6%, then this means mass of new particle should be larger than 3.3 tera-electron volts. These calculation and schemes are reported in these papers. Next is nuclear anapole moment. So now we consider the gamma 5 in the current of the quarks on the nucleus. Then its Hamiltonian includes the nuclear spin. So this is so-called nuclear spin dependent PNC effect. But this interaction also induces a nuclear anapole moment. This is due to the weak interaction between the nucleus. Okay, so nuclear unpolar moment is defined by these diagrams. So this nuclear unpolar moment is proportional to the nuclear spin. In history, sesame experiment shows the finite value of the nuclear unpolar moment, but these results are not overlapped. Therefore, someone should observe the nuclear unpolar moment again. So, therefore, we suggest the measurement of the nuclear unpolar moment using francium atoms, using the S to D5 half state, because these states include only the E1 nuclear spin dependent terms. Therefore, we cannot consider this large effect of the NSI terms. So, in this scheme, Professor Safwan thus also calculated these all matrix element for this nuclear spin independent PNC effect. So then we calculated the light shift for each hyperfine state for the francium atoms. So then finally, we calculate the total effect of the PNC. Then we obtain the 44.5 millihertz for the PNC-induced light shift. So now we compare these results. So for barium and radium ion have the less than 1 millihertz effect, but in francium, it is 14 millihertz. So this is too large to detect the unpolar moment. This is our final result. Okay. Finally, we briefly introduce our experimental situation. So we move the whole experiment setup from the north part of Japan, so-called Sendai, to the Tokyo. Okay, then we construct a new experiment apparatus to produce francium atoms. This is our experiment apparatus in the Riken. So the University of Tokyo CNS. We consider this oxygen beam interact with this gold target. Then this fusion reaction produce the francium atoms. Recently, we observe the francium atoms using this SSD apparatus. Then we estimate the number of francium atoms is 10 to 6 in per second. So this number is limited by our beam intensity. In future, we can increase the number of francium atoms by factor of 10 to 100. We expected. Okay. So finally, I introduced our collaborator, francium atoms, cesium atoms, Professor Das and Professor Safu calculate many theoretical values. So we appreciate Professor Das and Safu, and other people engaged in the experiment in the University of Tokyo and Tokyo University. And Professor Castova in Nice, France, also calculated for cesium atoms and suggested the optical lattice scheme. So I summarize my talk for PNC work. We obtained such a new result for the mass of the new particle for 6 tera-electron volt and 14 millihertz for nuclear unpolar moment. And this talk based on the many papers collaborating with Professor Das-san. So I appreciate Professor Das. So thank you for your attention.
Many thanks, Professor Aoki for an excellent presentation. The talk is open for discussion, and I can see Vijaya Sahu asking a question. How many Francian atoms can be produced in your facility? Are you planning to measure any other spectroscopic properties of Francium apart from the PNC?
Also, how many atoms?
Yes, Francium atoms. Yes.
Yes. So okay. Yes. So in Riken, we expect 10 to 8 atoms for francium. So this is very useful to decrease the uncertainty of the frequency measurement.
Thanks a lot for your answer. So I'm waiting for more questions to come because we still have about 5 minutes. So I would encourage the participants to ask questions by typing on the chat. So I don't see anybody typing. So let's all thank Dr. Aoki for an excellent presentation. And we go on to the next speaker. Well, yes. So I.
Okay, you're welcome.
Okay, thanks.
Okay, thanks.
The last speaker before the lunch break is Professor Koichiro Asahi. And the topic of his talk is electric dipole moment of diamagnetic atom 129 xenon as a probe for new physics. And he's from Riken, Japan. So welcome, Professor Asahi.
Thanks to Chairperson for kind introduction, and also felicitations to Professor Das for his 65th birthday. Can you hear me?
Yes,
Yeah.
yes.
Okay. Today, I would like to talk about the present status of the study of electric dipole moment of diamagnetic atom 129, xenon. Okay, the standard model nowadays is known to work excellently well to explain and predict the result of experiment performed on the ground or in laboratory. But there is some deficiencies in this standard model. The biggest one is that it cannot explain a major part of matter in universe. Only 5% is the standard model particles. Even further, the presence of matter in universe itself is a puzzle. CP violation within the standard model is too small to explain the predominance of matter over antimatter. Extra CP violation is really necessary. Thus, the EDM is an exclusively excellent new physics indicator, free from so-called standard model background. What is EDM? Maybe Professor Phillips already explained this morning, but maybe I will show my view. Okay, EDM from experimenter is the following. EDM is finite when the energy of a particle differs for between two different situations. Its spin parallel to electric field and anti-parallel. And the difference in energy is proportional to the strength of the electric field. Then it means that Hamiltonian for a particle under an electric field should contain a term like this. And this coefficient, d times sigma, is defined as electric dipole moment, d. And so we could model electric dipole moment naively as the two opposite charges separated by a distance a. And charge times this distance vector makes the EDM. However, D is quite peculiar in character. Under time reversal transformation, spin is reversed, but D, because it is purely spatial concept, it doesn't change. However, according to its definition, D should be always parallel to sigma. Therefore, D should be inverted as sigma is inverted. What can I do for this contradiction? We can say that EDM must arise from some T violating part of system's wave function. Therefore, EDM violates T, hence CP by CPT theorem. Relativistically, the interaction of EDM should be in a Lorentz covariant form. So it should be expressed in this form. And in fact, this coincides at the non-relativistic limit to d sigma dot E, that is the previous expression for D. Okay, but again, the problem is raised. Counting the mass dimension of this operator, this fermion, and the derivative of boson, that makes the dimension 5 that exceeds the natural number 4. And this suggests that this process should not be an elementary process and should involve some loop particle in this vertex. The lowest loop diagram in the standard model would be the electron turns to another particle, and then return back to the electron. But because standard model only contains one CP violating phase, this first vertex can involve this phase, but when it returns to the electron again, it should contain another opposite phase, and in total it cancels out. So EDM becomes 0 in this lowest order. Therefore, the standard model cannot explain no. A standard model predicts a very small size of EDM that is almost impossible to detect experimentally. In contrast, theories beyond the standard model allow more than one CP phase, so that the cancellation may not occur. Because of this reason, most of the models beyond the standard model allows size of EDM to be experimentally reachable. Therefore, if experiment finds non-zero EDM, this is by no doubt evidence for new physics. New physics appears in the above certain energy scale, and it appears in the standard model world as diagrams like these. With standard model language, lepton, quark, and gauge bosons. And then below the hadronization energy, the language is changed to be electron, nucleon, and gamma. And for each conversion, these are converted to the diagrams below the energy scale of hadron, and these connections can be quite established way. It can be connected. Finally, we experimenter can access only these particles, these objects, the bottom particle. I mean, they are atoms or neutrons or bare nuclei or ions. They are connected by atomic physics. For example, atoms, EDM of atoms are connected to the upper diagram by atomic physics. These particles are connected more or less by nuclear physics and hadron physics. So the nice point here is that if we know the size of EDM for these particles, then we can connect, we infer the strength of the coupling constant for upper level diagram. And finally, it can be connected to which models, new physics, model for new physics is right. This is a way that many experiments, studies of EDM has a way to the goal. Okay. These are this expresses the present status of EDM experiments worldwide. Newton, this is already Phillips presented, and this fantastic upper limit, new upper limit appeared. These are atoms. This is molecule, and this is other particles like muon, proton, and deuteron. They are charged, and only EDM is only studied in storage ring. Okay, so the subject for our experimenters are like this, and today's talk is confined to this one, the EDM of diamagnetic atoms. Okay, how to measure the EDM. This also is excellently presented by Phillips, but maybe just natural way of detecting the EDM is by definition to detect the difference in energy caused by application of electric field. So we measure first the energy difference between spin up and down states by measuring the transition frequency or spin precession frequency, and then apply the electric field parallel and anti-parallel, and find the difference in frequency for two cases. Okay. Now, some keys in the EDM experiment is as follows. The system must be electrically neutral. Otherwise, we cannot hold particles under the strong electric field. Exception is ring EDM. The particle in the storage ring is exposed to strong electric field, can be exposed to strong electric field, but because of the centrifugal force, it can stay there in the orbit. Then another key is that signal is very tiny, and it is in the huge background. So the experiment should be very careful dealing with magnetic field, because mainly the background comes from magnetic moment interaction. Spin do relax, so our time for observing spin precession is quite limited. Spins need to be polarized, otherwise the signal will not appear. Significant statistics is needed because the difference in frequency is not large, very small, and so requires a large number of particles, long measurement time, and high stability of the setup. Under this consideration, neutron is quite natural choice for measurement. And next one is the atoms. The paramagnetic atoms is sensitive to electric dipole moment, and also the electron-nuclear contact interactions that violate CP. Diamagnetic atoms is sensitive to nuclear shift moment, which I will explain later, and also the coupling constant, electron-nuclear coupling constant, that is of different type from this CS. Okay. Let's consider the group of point-like particles exposed to the external field. Hamiltonian is written in this form. The charge is Q, and it has electric dipole moment. So additional term appears here that comes from electric dipole moment interaction. But looking at inside this parenthesis, this is just the same as this Hamiltonian, and therefore Hamiltonian is re-expressed by this form with gradient times this small distance parameter, and finally it comes to this expression. This shows that the Hamiltonian is surprisingly the same as without EDM, Hamiltonian without EDM. But the shift is there in the position of particles. Okay, so the system of point-like particles with EDMs is just equivalent in Hamiltonian wise to system of point-like particles without EDM, but with their positions slightly shifted. Or we can say that the effect of EDMs possessed by point-like particles is totally cancelled by slight shift of their positions. This phenomenon is called shift shielding. Because of shift shielding, we should solve one problem. That is, in a diamagnetic atom, the EDM cannot be produced by electron because electron cloud is in a closed singlet state and no contribution to the atomic spin. And therefore, only nucleus can produce EDM in atom, diamagnetic atom, but EDM of nucleus never appear in atom because of the shift shielding. However, nucleus is not point-like, and a non-trivial spatial distribution of nuclear charge inside nuclear volume can induce an EDM in the electron cloud. Therefore, see this carefully. The nucleus, the outer layer of nucleus has upward polarized. I mean, the charge, electric charge is more here and less here. But inside inner part of the nucleus, it has the opposite EDM because this is slightly more charge here and less here. So the EDM, two EDMs cancels and totally nucleus doesn't have EDM. But because electric charge distribution is non-flat, non-uniform, so there appears strong electric field inside the nuclear volume in a form of this. So because of this electric field, electron penetrating into nucleus receives a large kick from nucleus and totally shift the electron cloud. And this is the EDM of diamagnetic atom produced by nuclear shift moment. The nuclear shift moment is defined in this way. Okay, so the measurement of EDM in a diamagnetic atom is just the measurement of shift moment, actually. This is mercury experiment. Mercury atom is atom where the most severest upper limit is posed. This is the setup used in this experiment 4 years ago. Essentially, this experiment uses the method to observe the spin precession of mercury by through the polarization plane of linear polarized light penetrating, passing through the vapor of mercury in this detector. Because it swings because of the precession, such signals will appear, and by sophisticated way, they obtained this stringent limit. This is 7.4 into 10 to the minus 30 centimeter. Okay, as for Xenon 129, we have been developing some special device which enables the spin precession to continue to maintain for unlimitedly long time. And actually, the precession is maintained for a very long time. This is 5,000 seconds, but this can be extended to unlimitedly. This uses a kind of feedback technique. I have no time to explain, but this is our setup, and our study is still not still at the developing stage, and we have still room to improve. Our goal is 10 to the minus 28 centimeter upper limit. Okay. Okay. But nice, good news is that recently the new result on Xenon 129 comes. There was two. One is Munich, Michigan, Berlin, Jülich group. They provided this improved upper limit, and then they even improved this limit, revised the data, and finally it becomes on the scale of 10 to the minus 28. And other group is Mainz, Jülich, Heidelberg group. They also improved drastically from this 19 years old upper limit. Okay, the first group used just this setup, and the point is that the spin relaxation time is surprisingly long, and because of this, they obtained this excellent upper limit. Okay, this is another group, and there are other atoms that can be measured. The EDM can be studied, and okay, time is approaching. Then, what can be derived from these measurements? Recently, these study calculated relativistic coupled cluster calculations and obtained the coefficient for theta, coefficient for diamagnetic atom electric dipole moment that is represented by shift moment and coupling constant for electron-nucleus interaction. The theta and the eta is obtained as this. And using this, the EDM of xenon is expressed in terms of shift moment and coupling constant CT. And if adopt the new upper limit, then the upper limit for shift moment and CT are obtained. Okay. Furthermore, the shift moment itself can be expressed by the CP violating fundamental constant G pi NN, pion nucleon coupling constant, isoscalar, isobector, and isotensor. And this is for sophisticated nuclear shell model calculation. They obtained these coefficients, this and this and this, and inserting this into the previous expression here, then it gives the expresses EDM of xenon 129 in terms of solely fundamental constant. And in this way, the experiment can do such studies. I mean, for neutron mercury, radium, for example, will be expressed in terms of these fundamental constants, and we could solve this coupled equation to determine these coupling constant individually. Okay, so in this way, many EDM studies will determine what new physics model will be the right model. This is the goal of these experiments. Summarizing, CP violation is a key concept in looking for an experimental evidence for new physics. Among CP violating observables, the EDM being background standard model background free is one of the strongest probes for physics beyond the standard model. EDM of a diamagnetic atom represents CPV in hadron sector through nuclear shift moment. Experiments searching for a diamagnetic atom EDMs are making rapid progress. By combining EDM results for different systems with the help of theoretical efforts in hadron, nuclear, and atomic physics, new theory beyond the standard model will be pinpointed. Thank you for listening.
Thank you, Professor Asahi, for your excellent presentation. The talk is open for discussion. I seem to have one query from Professor Minori Abe,
Yes.
but I cannot make out the meaning in English.
Pardon?
So it says the first word is IMA.
I-N-E.
The next word is a big word, GAIBUNOCATURY.
Sorry.
OCA.
I don't know. Yes.
Sorry.
Then OKUHA. Okay. There is a comment by Prasanna that it was simply typed by accident. Maybe the fingers went through. So this could simply be kind of a gobble something. So we do not seem to have actually any other questions. Okay, so Dr. Abe says that it's sorry, just an accident.
Okay.
But still we have about 3-4 minutes time. So I would encourage some participants to ask relevant questions. Since I don't see anybody typing, we want to close it then, and we all thank Professor Asahi for his talk.
Thank you for hearing.
This actually concludes the pre-lunch session, and I take the opportunity of thanking first Dr. Anil Bhardwaj, the PRL director, for inaugurating the conference, and then all the 4 speakers for their excellent presentations. And also thanks to the participants for asking relevant questions. So thank you all. And now we break for lunch. We come back at 2:30 Indian Standard Time. Thanks a lot, and we just wake up.
I just want to make a quick announcement that the Zoom room is going to be open. So those who want to leave, they can leave. Those who want to stay back are most welcome to be with us here. And see you all in another 1.5 hours. Thank you, Professor Mukherjee.
Thanks a lot.
So can I request, yeah, Professor Asahi, I request you to kindly, if you can stop sharing your presentation. Professor Asahi, can you hear me? Professor Asahi.
So maybe he's unable to
I
hear.
think, yes.
Oh
yes.
no, I don't know. I mean, his speaker is muted. So
Let me try if I can stop his, yeah, great. Thank you.
thanks a lot.
Stopped the screen sharing, so that's fine.
So we'll come back at 2:30.
Yes.
Yes.
So okay, Bindya will be okay.
Yes, I'm here.
So we'll be back by 2:15. So let others join later.
Okay.
Because we have to allow. Or I'll come back around 1:30 or something. 2 o'clock.
All right. Will it be convenient if I share that screen with the music, or you want it?
Yeah, you do that, but play with very slow music, slow sound.
Yeah, I'll do that. Okay. So hi, let's wait for another 4 minutes because the time is at 2:30 and it's still 2:26, and then we can start.
Hello.
Hello.
Hi, Professor Schmidt.
Hello, Professor Schmidt. This is Amitav Sengupta. So I shall be chairing the session. So we'll just wait for a few more minutes for
Absolutely.
others to join in. So Bindya, you will be passing on the YouTube questions to me on this chat box, right? Okay, good.
So how's the conference been so far?
Well, I think it's been going perfectly. Very nice. We had
Excellent.
4 excellent talks in the morning session. And there were quite a number of questions and comments. So far it's been going absolutely wonderfully. So,
Fantastic. I'm glad to hear that.
yeah, and we are looking forward to the afternoon session, so which is also packed. We have 5 talks.
Yeah, it's quite a dense schedule. I've noticed.
And because of the different time zones, parts of the world. Perhaps for you, it's early in the morning. Yeah, you've just.
Well, it's 11 a.m., so it's still okay.
Oh, okay, right.
But I missed the morning session for that reason, of course. Yeah.
That's right. That's right. Well, and for people who are in the US, it's really terrible because it's just 12 hours apart.
Do you record the videos?
But they can watch from YouTube later. That option we have. We are recording.
Yeah, but those people staying in the East Coast, for them, it's not so bad. They can still join in the afternoon sessions. For them, it'll be early morning.
Yeah. A very early morning indeed.
Yeah. Okay, Bindya, I think we can get started.
Yes.
Keep my introduction very short because that's not relevant for the proceedings here.
I'll try to do that. Okay, so I welcome everybody back to this post-lunch session of FSQT, and we would like to continue with the next session for the day. And it's a privilege to have Professor Amitav Sengupta amongst us. He's going to preside over the next session. Professor Sengupta is an expert in the areas of radio and atmospheric physics, electronics, atomic physics, time and frequency standards, with over 35 years of research experience. His major contributions include design and development of India's first atomic clock and the development of a prototype for the space-qualified rubidium clock for ISRO. He has also developed India's first satellite-based standard time broadcast using the domestic INSAT satellites. Professor Sengupta is a member of the first and second Antarctic expeditions in 1981 and 82, where he performed experiments related to upper atmospheric radio propagation and ozone studies. Subsequently, he was also the leader of a 100-member team of the 8th Indian Antarctic expedition in 1988-89, setting up the permanent Indian Antarctic Station Maitri. Professor Sen Gupta is a fellow of NASI, the National Academy of Sciences India, fellow of Institution of Electronic and Telecom Engineers, fellow of Meteorology Society of India, and a senior member of IEEE USA. He has received the O.P. Bhasin Award for Science and Technology in year 2002 for his significant contributions in the field of electronics and information technology. He also received the NCERT's National Science Talent Scholarship. And before I hand over to Professor Sen Gupta, I would quickly like to share the guidelines for the smooth functioning of the talks. Is that okay?
Yeah, please go ahead.
So we are going to keep all the participants mute all the time just to avoid any confusion. And the audiences who have joined us on Zoom, they can ask their questions by typing them in the chat window of the Zoom. Other participants who have joined us on YouTube are requested to send their questions along with their name and place, preferably on the chat window of YouTube. So these questions are going to be compiled by the moderator and sent to our chairperson, who's going to try to take up as many questions time permits. So over to you, Professor Sen Gupta now.
Thank you, Vindhya, for that kind introduction. Very good afternoon to all of you. Welcome to the second session of the FSQT 2020. Before we get started, let me just say that I'm very pleased and honored to have been invited to take part in FSQT 2020 and chair this afternoon session. I would like to thank the organizers, in particular Professor Vijaya Sahu, for inviting me. I'd also like to take this opportunity to wish my old friend, Dr. Bhanu Das, a very happy 65th birthday. Dr. Das, you have made seminal contributions to the field of atomic and molecular physics. I'd like to wish you very happy, healthy, fruitful years ahead. Given that you're still academically very active, let me just add that I'd very much like to be a part of the events that celebrate your 75th birthday and perhaps beyond the standard model. Having said that, now we get started with our session. We have 5 talks in this session by very eminent researchers in their respective fields, 4 keynote talks and 1 invited talk. I request the speakers to kindly keep to the allotted times. That enables us to allow questions. I was going to talk about the rules of the game as far as the questions are concerned, but Vindhya has already covered that. So we now move to our first presentation of the afternoon session. This is by Professor Pete O. Schmidt, who belongs to the Quest Institute of Physikalisch-Technische Bundesanstalt, or PTB, in Braunschweig, Germany. He also is affiliated to the Institute for Quantum Optics, Leibniz Universität, Hannover, also in Germany. Professor Schmidt's main area of work is quantum logic spectroscopy. His group develops and employs quantum logic schemes for precision spectroscopy of laser-cooled ions in Paul traps. So Professor Schmidt is going to talk about optical clocks with highly charged ions for tests of fundamental physics. So over to you, Professor Schmidt. You have 35 minutes of presentation. If you like, I'll give you a gentle reminder at the end of 30 minutes and followed by 10 minutes of discussion. So, Professor Schmidt.
Great. Thank you very much for the kind introduction. And let me also join in thanking the organizers for inviting me to this fantastic conference, and also in wishing Professor Das the best for his 65th birthday. Okay, let me get started. Now, there are a number of fundamental questions, open questions in physics. And among those are the question, can we unite all 4 fundamental forces in a unified framework? Currently, we do not even know what most of the universe is composed of, because we don't know what dark matter and dark energy are. We can only explain 5% consisting of normal matter in the universe. And we don't even know why we exist, because we have currently no model that explains the apparent asymmetry between matter and antimatter observed in the universe. Now, looking at these grand challenges or big picture questions in physics, we can expect to find answers by going into cosmology, producing better models of cosmology and what the universe is composed of. Or we can go to high energy physics to probe for particles that are not yet included in the standard model. And what I'd like to advertise to you, and this is, I guess, one of the themes of the entire conference here, is that we can go into the low energy, high resolution regime, where we can do quantum optics tabletop-like experiments and take advantage of the extremely high resolution and accuracy that is achievable with these experiments to find sort of an afterglow of these high energy and large scale questions in and their effects on atomic physics. And in my talk, I would like to particularly advertise that highly charged ions are very sensitive probes to new physics effects. Now, in my presentation, I will give you a very brief introduction into the physics of highly charged ions. I will show you state-of-the-art generation and spectroscopy of highly charged ions. I will then show you our setup that we've set up at PTB to perform coherent laser spectroscopy of highly charged ions. I will then show you how we slow and cool the highly charged ions, how we prepare them, and then show you quantum logic spectroscopy results. I will then end with a summary and tell you about our future plans. Now, if you're used to neutral atoms or singly charged atoms, then you have to readjust your energy scales when going to highly charged ions. Now, if we move, for example, from a neutral hydrogen to hydrogen like uranium, which is uranium 91 plus, then the binding energy of the last electron goes from 10 eV roughly to 140 kilo electron volts. The hyperfine splitting goes from micro electron volts to electron volts. So it's a transition in the visible wavelength regime. And QED effects contributing to the binding energy of the last electron scale from micro electron volts to 300 electron volts. At the same time, effects that we usually do not like when building optical clocks, such as the Stark shift, for example, is strongly reduced. And this is a consequence that is illustrated in this sort of artistic picture, where we have here the large electron s orbital surrounding the single proton in hydrogen, which is much more compact in the case of 91 or uranium 91 plus. And the much smaller electron cloud leads to reduced polarizability effects, for example. And that's good for optical clocks because that reduces systematic shifts. Now, to give you a more specific example, let me show you the system that we're working with. It's argon 13 plus, and it has the electronic structure of neutral boron. Now, in neutral boron, we have a fine structure split ground state with a fine structure splitting of around a few hundred gigahertz or so. And the first dipole allowed transition, P2S, is at 250 nanometers. If we now keep the electronic structure but change the nucleus, then that fine structure splitting is increased such that it now is an optical transition at 441 nanometers, whereas the first dipole allowed transition is at 19 nanometers, where we currently have no laser sources available for cooling or detection, for example, which is an ingredient that we would need for high precision spectroscopy. Now, for spectroscopy, for optical spectroscopy at least, at the highest resolution, we want optical transitions. And in highly charged ions, you can find those as fine structure transitions, such as here, hyperfine structure transitions, or hyperfine transitions if you go to higher charge state. And then there are level crossings where you can also find nearby levels as a function of the charge state that then are bridged by optical transitions. Now, what are the applications of highly charged ions? They have been investigated for many decades now, starting in the 50s or so, or even earlier. One fact about them is that they're very abundant in the universe because most of the matter in the universe around stars and inside stars occurs actually in a highly ionized form because of the extremely high temperatures in these systems. And what you can see here are iron coronal lines around our sun observed during a total eclipse. Of course, these are false color images, but from those you can determine the temperature and magnetic field, for example, around the sun. And so highly charged ions have been used as probes for cosmic and stellar processes. For the same reasons, they have also been used as diagnostic tools for plasma physics. Here you can see the charge state distribution of tungsten as a function of the electron temperature. So if you measure the charge state distribution, you get the temperature of an electron plasma, for example. Now, what many people may not know, but we won't have the next generation of these without highly charged ions, simply because the source in the latest wafer stepper machines, for example, from ASML here, is highly charged tin droplets, tin 12 plus, that emits at 13.5 nanometers and is employed here in these wafer stepper machines for optical, for the photolithography, essentially, of the latest chip generations. Now, these are not the reasons why we're interested in highly charged ions. We're interested in them because they offer a fairly simple electronic structure, and therefore they're a test bed for atomic structure theory. In particular, because we can compare it with experiment. Now, what has been done for a long time now is people have performed QED tests by comparing G-factor measurements with highly accurate QED calculations, and that's a test of QED in strong fields. Now, about 10 years ago or so, people have realized that highly charged ions can be used for more than just G-factor measurements, because they're also the highest sensitive of all atomic species when it comes to the sensitivity to a change in, for example, the fine structure constant. They're also extremely sensitive for probing local Lorentz violations or violation of local Lorentz invariance. I will talk later to you about isotope shift measurements that probes for fifth forces where they can be sensitive. They also potentially can be used to probe for parity violation, XUV transitions. And since the electronic cloud is very close to the nucleus, by performing spectroscopy on the electronic shell, we learn something about the nucleus. So all nuclear interactions with the electron cloud are amplified in highly charged ions. And there's many more things that one could imagine in this context. Okay, let me give you one specific example that you will learn or have learned already in the morning session more about, which is dark matter. Now, we know from cosmology that dark matter exists, for example, from galactic rotation curves, but we don't know what it is. And in its simplest form, and this is really just a very simple picture that I'm presenting here, dark matter could be a scalar field that is either extremely light, so the mediated particle is extreme light, and then we would have an oscillating field, for example, or it could be a topological field, so that it forms clumps. That, for example, our spaceship Earth passes through on its way through the galaxy together with the solar system. And we would then see transient effects of dark matter interaction with normal matter. Now, that directly leads me to how can we actually detect dark matter. And what we have to assume that there's a very weak non-gravitational coupling between dark matter and normal matter that we haven't found yet. Yeah, so we couldn't point our fingers to what nature this interaction would actually be. But what we do know is if that interaction exists, then it would change the level, the energy levels of our favorite two-level system, for example. Yeah, in the presence of the field, the energy level splitting here would be different. And we would interpret this, for example, as an apparent variation of fundamental constants, such as the fine structure constant or the electron to proton mass ratio, for example. And there's an excellent review on these types of effects that you can find here. Now, if we can boil it all down to a change in the variation of constants, then the next question is how can we measure such changes? And so what we can do is we can take our two favorite ion atomic clocks, for example, and we can compare them to each other. And we can calculate how their transition energies change as a function of a relative change in the fine structure constant. And that change is given by the sensitivity coefficient K here. And that gives essentially the relative change of the transition energy depending on the ion species and the transition under observation. And if we can now compare two optical clocks with very different K factors, we can put bounds on a possible variation of the fine structure constant by observing no change in the relative frequency between the two different ion clocks. Now that has been performed in the past using, for example, these systems here that have sensitivity coefficients in a single-digit regime, positive and negative. And this is a very preliminary plot where everything outside this white ellipse here is excluded. So here you see a relative change in the fine structure constant and a relative change in the electron to proton mass ratio. Now, if you want to zoom in here and find out whether this is actually compatible with zero or not, then you need to either measure for a longer time, improve the accuracy of the available clocks, or use systems with a much higher sensitivity coefficient kappa, K here. And as it turns out, highly charged ions have significantly orders of magnitude larger sensitivity coefficient than those of the ion or atom species that have been used so far. And this is part of the motivation for our work because we want to make these systems available for such searches. Okay, now, of course, what you have to do then is to be competitive with these measurements, you need to have highly charged ions as optical clocks at the level of current optical clocks. And the question is, can we do that? One mandatory requirement here is that highly charged ion species need to support very low sensitivity to resonance shifts. And what are these effects that can lead to such shifts? It's essentially electric and magnetic fields, collisions, and other effects. And yes, indeed, there's actually an advantage in highly charged ions because some of these shifts are actually suppressed. So the linear Stark shift, although not very relevant, is suppressed. The second order Stark shift, which is related to the polarizability, is strongly suppressed. The linear Zeeman is about the same as in neutral atom and singly charged ion species. The second order Zeeman is strongly or can be strongly suppressed, and the electric quadrupole shift, which is also a shift in ion optical clocks, is also strongly suppressed. And so you can see there can be some advantage in using highly charged ions, but these are, of course, not the only requirements. You also need to have suitable transitions in a suitable wavelength regime and so forth. And all these requirements for optical clock species can actually be fulfilled with highly charged ions. So they actually are very good optical clock candidates, with the added feature that they are very sensitive to these new physics effects. Now, then let's have a look at the state-of-the-art spectroscopy with highly charged ions prior to our experiment. And what was usually performed back then was so-called plasma or in-EBIT spectroscopy. So what you see here is a real-world picture taken with a camera of argon-13, an argon-13 plus plasma inside a so-called electron beam ion trap, where argon-13 plus is produced by electron beam bombardment. Now, the fluorescence from electron excitation of this radiation of 441 nanometers is then imaged onto a grating spectrometer and then imaged via a camera, and you get then images, calibrated images like those, where you have here the wavelength and then the count rate in a certain frequency band, and you can see nicely 4 transitions in the from the argon-13 plus that have line widths on the order of 45 gigahertz that you can resolve down to 150 megahertz. Now, why are these transitions so broad? The reason is the temperature in those electron beam ion traps is millions of kelvins, and that's it's electron volts, and that's just the wrong unit for high precision spectroscopy. So therefore, one of the problems here is then to enhance this resolution is that the electron beam ion trap is not the best environment to do high precision spectroscopy. And another problem is that I've mentioned before, there's no cycling transition available for cooling and state detection in argon-13 plus and actually in most highly charged ions. And this is a mandatory requirement for high precision spectroscopy, because that's what we typically do on a regular basis in ion clocks, where we trap singly charged ions in, for example, linear ion traps, as shown here, where we apply a radio frequency electric field on these blades here, and then apply a DC field to these end cap electrodes, and that provides a 3D harmonic confinement to the ions inside the trap at trapping frequencies on the order of a few megahertz. That enables us to perform recoil-free absorption spectroscopy or fluorescence spectrum. So the photons from the probe laser do not change the motional state, and it's also a mandatory requirement for high precision spectroscopy. We can have very long interrogation times because the ions live for hours, if not months at a time in the trap. The ions are trapped near the zero field of the trap, and therefore we only have very small trap-induced shifts. And we can isolate them from the environment in a ultra-high vacuum chamber, and we can apply laser cooling, and there's no other interactions except the Coulomb interaction, which results in a very high achievable accuracy, as for example, demonstrated in the Attribution single ion clock that has been demonstrated and is operated by Niels Huntemann in the group of Eckhard Pike in the building actually right opposite where I'm sitting. Now, how can we combine those features? And the solution is actually quantum logic spectroscopy, where we trap our spectroscopy ion, the highly charged ion, together with a logic ion that we can laser cool and have very excellent control over. And so we have a very strong Coulomb coupling between the two ions, which leads to a very strong motional mode coupling of the ions. And we can then sympathetically cool the highly charged ion using the beryllium logic ion. And we can transfer the internal state after spectroscopy using a series of laser pulses from the highly charged ion onto the logic ion, where we can detect it with very high efficiency. So in a way, quantum logic spectroscopy can be viewed as a composite system where we combine the advantages of both species and which allows us to investigate previously inaccessible species. And highly charged ion spectroscopy is not the only application, but quantum logic spectroscopy has been demonstrated with the aluminum ion clock for the first time, and currently the latest generation of these aluminum clocks that we're also building one is the most accurate clock in the world, operated at least in Boulder currently. And also molecular ion spectroscopy has been performed using quantum logic techniques. Okay, now let me show you our setup that we've built in a very close collaboration with Jose Crespo's group from the MPIK in Heidelberg. We've set up a cryogenic supply system to have a cryogenic vacuum here that we need to enable long lifetimes of the highly charged ions. We then built a compact electron beam ion trap using permanent magnets, where we have an electron gun that produces a focused electron beam focused by the magnetic field here, and then here in the center we leak in argon gas that is then ionized and produces predominantly argon-13+. We can then extract the highly charged ions, slow it down, and inject it into a cryogenic pore trap that we've set up, where we have pre-trapped a cloud of beryllium ions that we can laser cool. And then we inject a highly charged ion that we see as a dark void in here, and then we can start spectroscopy. Now let me just very briefly go through the sequence. We breed highly charged ions, do a time of flight to select argon-13+. That enters then a slowing region that is switched off when the highly charged ions are in the center here, which slows and cools the highly charged ion bunches, which then enter the pore trap as a last step. Now, you can see here this last step where they climb a last potential hill, and then we ramp up an electrode, and then the highly charged ions oscillate back and forth in the trap until we see an event like this, where a highly charged ion enters the Coulomb crystal of beryllium ions, and then we can apply parametric heating to prepare this 2-ion crystal here of argon-13+, together with laser-cooled beryllium ion. Now, the total preparation time is a few minutes, and the lifetime of the argon-13+ ion is on the order of 40 minutes, roughly. We can then apply sympathetic ground state cooling to the beryllium ion. Since the motional mode of the 2 ions is strongly coupled through the mutual Coulomb interaction, we sympathetically cool the highly charged ion also close to the motional ground state, corresponding to temperatures on the order of a few microkelvins, actually. That's probably the coldest highly charged ions in the universe, as far as we know. Okay, now I just want to briefly show you the state transfer sequence that we have. So we have here the electronic ground state and motional ground state. So these N's are the motional levels of the 2 ions in the trap. We then apply a spectroscopy pulse that generates an electronic superposition of ground and excited state in the highly charged ion. And for a regular optical code, we now detect the internal state, which we can't do on the argon-13+. And so we apply a logic pulse, what we call a red sideband logic pulse, that transfers this electronic superposition into a motional superposition of the highly charged ion, of the motional mode, actually. That is a joint motional mode between beryllium and argon, being in the ground state and in the n=1 excited state. We can apply the same trick on the logic ion and reverse this motional mapping into an electronic mapping on the beryllium ion, where we can then detect using state selective fluorescence for example, the ground state population, which is a one-to-one image or correspondence, which has a one-to-one correspondence to the initially prepared spectroscopy superposition. Okay, we've done that, implemented that with argon-13 plus using beryllium as a logic ion. You can see here the detuning of the spectroscopy laser, which is actually locked to the silicon cavity stabilized laser in the group of Eric Benkler and Uwe Ster, which is one of the best lasers in the world currently. You can see here nicely a scan across the resonance and an excitation probability that that has a width and a contrast that is strictly Fourier limited here. We can also put ourselves at the center of the resonance and then vary the probe time. And what you see here is Rabi flopping on the resonance of the transition with a dephasing that is dominated by the excited state lifetime of around 10 milliseconds. We've also performed a dedicated lifetime measurement, which agrees very well with previous in-orbit measurements. Now, I have not been telling you the full truth. Of course, it's the transitions are, it's not a two-level system, but rather we have 6 levels. And so we have overall 6 transitions in this fine structure manifold from the P1 half to the P3 half transitions. And you can see here all 3 transitions zoomed out together with theory comparison. So we take the outermost transitions as a calibrator for the magnetic field, and then we have the dashed lines here are the Landé G factors. We can then go from this semi-classical theory to relativistic Dirac theory, which is the violet dashed lines that still does not match. If we include electron interactions, then the match actually gets worse, and only if we do the full QED relativistic calculation, you get a perfect match when you zoom onto the lines. And if I say we in connection with calculations, I do not actually mean we, because that has been done by the group of Shabayev, and the G factor measurements or calculations are actually published in this publication. Now, we can measure using our technique ground and excited state G factors currently with a resolution below 10 ppm. And you can see a comparison between the theory values and our measurements here in blue. And using our measurements, we could clearly rule out these theoretical predictions up here. Okay, now I've promised you optical clock operation, and we've also operated our highly charged ions as a clock. And for this, we have stabilized the center frequency of our laser using a so-called 2-point sampling technique on the center of these 4 lines that are signified with the red dots here. And you can see a time trace of the lock servo steering the laser frequency onto these resonances on this side here. And if we take an Allen deviation of this time series, that gives us sort of the averaged fractional frequency uncertainty over time. So here's the averaging time, and here's the fractional frequency uncertainty. Then you can see here that if we average over the magnetic substates, we average nicely down, despite the fact that the magnetic field.
Professor Schmidt, would you like to wind up in a few minutes?
Excellent, thank you. We had a magnetic field step here at that time, which averages down if you average over all magnetic fields or over all Zeeman components. The average is down very nicely. Okay, now how does our frequency measurement compare to previous measurement over time? You can see that we have here the evolution over the years of the relative accuracy of the argon-13 plus measurements. There's been a recent measurement in Sven Sturm's group at the NPIK in Heidelberg, and our measurement is down here at 0.3 Hertz, and we're currently aiming towards going to the 10 to the minus 16 regime and below. So that's a 8 to 9 orders improvement over the previous results. Now let me summarize briefly. I hope I could show you that we can do precision spectroscopy in highly charged ions to address fundamental physics. We have now achieved full quantum optics control over highly charged ions. I've demonstrated you the first coherent spectroscopy, and we applied them to measure excited state lifetimes and the G factor. And a beauty of this quantum logic technique is that it's actually quite universal, so we can just exchange the argon 13 plus with another highly charged ion. And the main infrastructure that we've set up is actually around the beryllium ion system. And so we just need another highly charged ion and a new spectroscopy laser to perform highly charged spectroscopy on another highly charged ion. So that's what we want to do in the future. We want to demonstrate the true first optical highly charged ion clock on this argon line. We want to do a full evaluation of systematic uncertainties that we're currently working on, and then perform absolute frequency measurements. We also want to verify calculations that we have performed, or rather that have been performed in Andrei Sushikov's group between argon 36 and argon 14 of this fine structure transition. And now the next big thing in terms of fundamental physics questions is that we want to address is isotope shift spectroscopy. And let me just show you 2 slides on this. Where does the isotope shift come from when you go from one isotope to the next? We have 2 effects, which is called the field shift. That's the overlap with the electronic wave functions and the nucleus, and the recoil shift here. And if you use 2 transitions, you can eliminate the not very well known change in the nuclear charge radius, and that gives you typically a straight line according to this first order approximation. Now, if you now had an additional field that would couple quarks, specifically neutrons, to electrons, then that with a certain coupling to neutrons and electrons that can be combined in this alpha nu physics parameter, then that would show up as an additional factor in this equation that I just introduced to you, and would lead to a nonlinearity in this linear King's plot. This is not actual data, but this is sort of how it would look like, just to sketch. And by not observing this deviation from linearity, we could constrain new force carriers that are shown in this plot here. This is essentially the coupling strength between neutrons and electrons, and this is the mass of the new force carrier. And here are predictions and measurements, actually. So this is a calcium measurement with 20 Hertz. And if we performed this type of measurement, combining singly charged calcium with highly charged calcium transitions, then we would improve these constraints by 3 to 4 orders of magnitude, because we believe we can go even below 20 Hertz here. However, we need to be cautious and sort of subtract higher order standard model nonlinearities that need to be taken into account here. And so these are our future goals. Besides isotope shift spectroscopy, we want to investigate other clock candidates that have been proposed by one of the chairs of this conference, Vijaya Sahu. And we also want to investigate alpha sensitive level crossings, for example, praseodymium 9+, iridium 17+, or highly charged californium transitions. And there's many more things that we can do with highly charged ions, and we're looking forward to explore those. Now, of course, I have not been doing all of this, but rather my excellent team here, Peter Micke, a senior postdoc, the entire group is led by Stephen King and former PhD and postdoc Tobias Leopold, and we have now a new PhD student, Lukas Spies, and a strong collaboration with Jose Crespo's group. And with that, I'd like to thank my excellent team and you for your attention.
Thank you very much, Professor Schmidt, for that excellent talk. I have a few questions here on the chat box. So there was one question by Professor Vijaya Sahu, but he has withdrawn it because you've already mentioned what he wanted to ask. So there's a question by Sandeep Dubey. What can be a possible candidate for interaction of dark matter with normal matter apart from gravity?
Oh, I think the next speaker is probably better posed to answer that question.
Okay.
He's going to address it in his talk, I guess. Hi, Dima.
Okay, all right. So the next question by Satyajit Saha. What would be the effect of Doppler broadening and shifts on these high precision measurements with HCIs? How is it controlled or eliminated?
Typically what we do is sympathetic cooling, and this is washing some dirty laundry, I should say, because on paper sympathetic cooling works perfectly well. Yeah, so the ions should have should be in the same motional mode. However, there's a problem with the coupling strength. Yeah, so if I want to illustrate this, yeah, the radial modes, if this is my beryllium cooling ion and this is my highly charged ion, then they're separated by tens of microns. And then there's one mode where the beryllium ion moves a lot, and then there's another mode where the highly charged ion moves a lot, and the beryllium moves only very little. And that specific mode is not very efficiently cooled. And if you then have an initial heating rate, just some arbitrary motional heating rate in your system, that leads to a steady state temperature that is not necessarily very close to the ground state. And we're currently in the process of investigating the efficiency of that cooling in the presence of additional heating rate. And it looks actually very promising, such that this will not be a limiting effect in our system.
Great, thanks. There's one more question that I can take. This is by Jasmine Gogda. How to obtain energy levels of a doped element unknown in a host material theoretically? I don't understand how this is relevant to this talk, unless...
I'm not so sure. Maybe that's a remainder for a question of one of the previous talks.
No, it isn't. But anyway, I'm not sure this is relevant to this particular discussion. So one final short question. Aishik Acharya says, what would be the stability of such an optical clock compared to the conventional optical clocks?
Yeah, so that's a very good question as well. And we believe, and I showed it already to some extent in the preliminary data, the stability will be very similar to other single ion optical clocks. We don't expect too much overhead due to the fact that it's a highly charged ion. But we still have to live with the fact that it's just a single quantum absorber that we are probing, and therefore has limited statistical uncertainty compared to, for example, optical lattice clocks, where hundreds of atoms are probed at the same time. And the only way we have around this is to actually probe for seconds, yeah? Because the longer you probe, the longer your coherence time is, and that will reduce your statistical uncertainty. And so we expect to be able to probe these highly charged ions for seconds and then reach statistical uncertainties that are below 10 to the minus 15 in 1 second, and would allow us to resolve, let's say, 10 to the minus 18 with several hours of integration time. Yeah.
Thank you. Actually, I noticed that the lifetime of your Argon 13 Plus was just about, you mentioned 40 minutes or so, with a vacuum level of 10 to minus 14 millibars.
Yeah.
So this has to be improved, right? In order for this.
Not necessarily. Yeah. So other single ion clocks, like the aluminum clocks, there the ion lifetime is not much longer than this. But you're right. Yeah, it would be much more comfortable if we had longer ion lifetimes. And we're currently working on it and investigating how to improve the vacuum conditions in our system.
Great. Well, with that, we have to come to the end. Thank you very much again, Professor Schmidt, for that excellent talk. Thank you. So
yeah, thank you very much for having me.
So you'd like to unshare your presentation, so we move to the next talk. So we move to the next talk now by Professor Dmitry Budka. He's from Helmholtz Institute in Johannes Gutenberg University in Mainz, Germany. The area of research that the group of Professor Budka focuses on relates primarily to testing fundamental symmetries of nature in experiments which utilize the methods of atomic, molecular, and optical physics. Today is going to talk about new and recycled ways to look for dark matter. Professor Budka, you have 35 minutes for presentation and followed by 10 minutes of discussion. Over to you, Professor Budka.
Professor Budka, you have to unmute yourself. I mean, I see you are muted. Let me do it. I can.
Yeah, I think you can do it.
Okay, good. Now you should hear me.
Yes.
Okay. Thank you so much. May I ask, Mr. Chairman, that you give me a 5-minute warning before my time is.
I will.
Thank you. Thank you so much. So I'm really grateful for this opportunity to give a talk at this meeting that is celebrating Professor Das' 65th birthday. And I must say, let me see if I can advance the slides. That I have known Professor Das for many, many years. I think we first met in Berkeley in the early 1990s and began friendship and collaboration that lasts till this day. And Professor Das was the one who first invited me to India and organized actually several trips over the years that I made to India, and there are a couple of pictures. This one is in Bangalore in 2005, when I spent some time at the Indian Institute for Astrophysics, where Bhanu was the director at that time upon his invitation. Here's his wonderful family, as you probably some of you know. Then that visit to India actually introduced me to a large number of wonderful scientists in India. For example, you see here Sadiq Rangwala, and this became sort of the beginning of a lot of, I would say, lifelong friendships and collaboration. Then this is a picture taken in another trip to India that I made in 2013. And next to Bhanu, you see another old friend and collaborator, closely related to Bhanu. This is Professor Dilip. Anyway, that was actually a super memorable, one of many memorable meetings in India. And you here see Philip, one of the speakers, and many others. I should say I'm going to stop the slideshow, I mean the presentation of the photographs, because I want to get to science, but I have a lot more. And if you want to see them, ask me a question after the talk. But now to science. We have an obvious problem in modern physics, and you can call it an elephant in the room. This is that we don't know what most of the matter is. But actually, this is not the only big elephant in the room. There are others. we do not really understand the matter-antimatter symmetry observed in the universe. We don't know why. There is roughly similar amount of matter and antimatter in the universe. We do not know why strong interactions seem to respect CP symmetry, even though it a priori should be straightforward to introduce CP asymmetry in the theory of strong interactions. We have a hierarchy problem that the particles appear at masses that are many orders of magnitude smaller than the natural scales of physics, like the grand unification theory or weak unification scale, and not to mention dark energy. So it would be highly appealing intellectually if actually at least some of these elements, and better all of these elements, actually would be one elephant, which is basically something that would explain everything. And in fact, there are such candidates that would be, if we find them, that could potentially explain many of these problems. So now let's discuss quickly what dark matter could be, or what could be sort of something that makes us think there is dark matter. And actually, I apologize to the audience for repeating a lot of things that maybe I said before, and of course many others said before, but I would like to give this quick introduction before I tell you about the most recent stuff in our lab. Anyway, again, appealing would be to say that maybe there is no dark matter, but it's just that we don't understand gravity on large spatial scale, and the modified Newtonian dynamics theories attempt to do this. Unfortunately, I'm not an expert here, but it seems that they are not doing super well at the moment, or some of them actually still require dark matter if you follow them consistently. There are other ideas for how to get rid of dark matter, and I recently participated in exploring one of them, which is actually seeing if a finite mass of a photon can potentially explain at least the dark matter in the galaxies through the modification of electromagnetic equations, the Proca magnetohydrodynamics. Again, this was exciting in the beginning, but as we developed this theory, it turned out that this is at least not the whole story. Black holes, dark planets, interstellar chaos, and of course, weakly interactive massive particles have been considered. In fact, this has been the dominant paradigm for dark matter for many years. Even though you hear people say that it is not doing very well, this is actually not quite true. There is still a nice a range of masses for WIMPs that are not excluded, and it is doing quite well. But still, people have been looking for it for decades, and there is not yet a sort of undisputed evidence for them. And so, relatively recently, a large and important class of dark matter candidates came to prominence, and these are known as a collective name, ultralight bosonic particles. And I can explain, but won't, unless you ask me in the question time, why being ultralight means that they have to necessarily be bosonic. This is maybe at the first glance an unusual connection. How does the mass of the particle relate to its spin properties? But yes, there is this connection, which is pretty straightforward, and I will explain it if you ask me in the question time. So these bosonic particles that have to be abundant if they are ultralight, and therefore can be thought of sort of not individual particles, but fields that fill the galaxies. They could be of different spins. So, for example, they could be spin 0, and axions are pseudoscalar with negative intrinsic parity, or a generalization of these, which is also known as axion-like particles. They are also pseudoscalar, or scalar particles like dilatons, vector particles like, for example, dark or hidden photons, or tensor particles, or whatnot. Now, there is yet another paradigm, which is sort of the opposite from all of these here. And this is an anti-quark nugget paradigm, and I will try to explain what this is. And this is very, very interesting, and a sort of orthogonal to the notion that dark matter interacts weakly with itself. The dark matter in the form of anti-quark nuggets interacts maximally strongly with matter, and yet it could be a dark matter. So I'll try to explain this. And I'm involved personally in searches for different kinds of ultralight, bosonic particles, and most recently also in the nugget search. So I give you a couple of examples of what we're doing. One is trying to look for pseudoscalar dark matter using nuclear magnetic resonance. And because we're trying to do these searches as sensitive as possible, we are approaching the quantum limits, and this is where we want to be, sort of at the quantum limit of measurements. So the idea of the cosmic axion spin precession experiment, or CASPER, is that if there is this pseudoscalar dark matter, axions or axion-like particles, then they can have two effects that theory predicts. One is that these fields should induce an electric dipole moment of particles, specifically nuclei, but not sort of a permanent electric dipole moment in the sense that it's static in time, but a dipole moment that would oscillate at the frequency given by the Compton frequency of the underlying particle. Then what we can do is we can prepare a spin polarized ensemble of nuclei in a magnetic field, and then apply a strong transverse electric field. And the axions will induce a dipole moment of the particle, and the interaction term of the spin with the electric dipole moment then will create sort of an analog of a magnetic field that oscillating perpendicular to the leading field. And when the frequency comes to resonance with the Larmor precession frequency, then we will have a spin flipping that we can detect with the methods of nuclear magnetic resonance. And this electric field interaction we call the version of the CASPER experiment looking for this interaction is called CASPER electric, and it is located physically at Boston University in the laboratory of Professor Alexander Sushkov. There is another version of this experiment, and it relies on another interaction of the axions or axion-like particles, and this is so-called a gradient interaction. Here, we do not actually need to apply any electric field or any other fields, and we rely on the spin interaction with the gradient of pseudoscalar field, which itself acts as a magnetic field, once again oscillating at the Compton frequency of the particle. And there is actually a series of these experiments, and the headquarters of this is our laboratory in Mainz. And so this just is an illustration that when we have the dark matter inducing the precession in the presence of the strong leading field, we detect this precession with some sort of a magnetometer, typically a superconducting quantum interference device. Now, the Casper experiments are still fitting in one room. These are not huge experiments, but they are sort of involved. And in the meantime, it turned out that we were able to get first results at least for the Casper wind experiment using an unusual kind of a nuclear magnetic resonance, which is zero field magnetic resonance. And here it's really quite interesting and exotic from the point of view of NMR experts, because instead of a strong magnet that we usually use in a nuclear magnetic resonance experiment, we actually have to use a fancy magnetic shield to get rid of even the field of the Earth. Anyway, this setup turns out to be a very interesting area of nuclear magnetic resonance, and we have very nice and strong signals. And because we work at low field here, we were able to look at extremely light pseudoscalar particles. And to give you an idea, here is an exclusion plot, which is typical for working with this bosonic dark matter. So here you have the you have the mass of the particle in electron volts, and we're talking about from 10 to minus 13 all the way down to 10 to minus 22. And 10 to minus 22 corresponds to a very, very slow oscillation frequency with a period on the order of a year. So such a slow frequency. So it's given here, the logarithm of the frequency is given here on the upper axis. And this is a coupling constant that characterizes the strength of the interaction of dark matter with nuclei, assuming that this particle constitutes all the dark matter. And so we were very happy to get some results just very recently, 2 papers published last year. And in the course of this work, we realized that one has to be extremely careful about particularly this low frequency region. And that has to do with statistical properties of dark matter. The analogy we like to think about here is sort of you're all familiar with the speckle that arises when you have a laser beam scattered from some random surface, for example, and this is sort of a sequence of bright and dark spots. Likewise, the dark matter can also show the regions where there is large intensity of the field and weaker intensity of the field. And such a picture, it changes in time, but the persistence time is the coherence time of dark matter. And it happens to be, for the reasons, again, I will be happy to explain in the question and answers, but I don't have time to explain at the moment, but it's about 10 to the 6th period. And so here we are talking a period of about 1 year. And suppose you do a measurement and you see nothing, then that could be because there is no dark matter at this frequency, and it could be because you're not very lucky and you measure when you are sort of in the dark spot, and then you have to wait 1,000,000 years to do your experiment again to discover this dark matter. So these aspects are very important. So I must say that in addition to this NMR technique, there are some other ways to look for this type of dark matter. And my colleague Min Jiang in USTC in China has set up a beautiful maser-based experiment that is described in this paper here, and is now using it to do very sensitive searches about in the millihertz range of the field of the frequencies. It's a very interesting quantum system with all kinds of interesting dynamics, but I have to move on. In the meantime, the sort of the main Casper experiments, both Casper Electric and Casper Wind, are coming into operation. So this is some pictures from Casper Wind, and in fact, Casper Electric has already has some preliminary results that we are about to publish or submit for publication in the coming weeks. Let me now turn to searches for scalar as opposed to pseudoscalar dark matter. And the ideas here go back a few years. So dilaton is a scalar particle that is predicted by string theory. And Asimina Arvanitaki, shown here, and her younger colleagues a few years proposed that the dilatonic field can have an effect that they apparently changing the values of fundamental constants. And in particular, the energy intervals that determine the frequency of atomic clocks can be affected, and they propose to look for temporal oscillations rather than monotonic drift of atomic clocks frequencies, atomic clock frequencies in comparison. And when this proposal was published, Nathan Leifer, a postdoc at that time in my group, immediately realized that we actually have an experiment ready to do this, which is a very beautiful system of atomic dysprosium, where there are two levels of opposite parity that are very close, and this provides quite an unusual situation in atomic physics that we exploited in a large number of precision experiments. And in fact, Nathan, this is his picture here, realized that not only that, but that we don't even need to do any new measurements, because we already have all the data stored on disk, because we were looking before for slow drift, monotonic drift of fundamental constants using dysprosium, and now all we needed to do is go back and reanalyze it for the presence of oscillations. And we did this. This analysis was spearheaded by Ken van Tilburg, who was then a graduate student at Stanford. And we published these limits from dysprosium, and in our paper, we pointed out that if you actually do a dedicated series experiment with state-of-the-art clocks, rather than recycle some old data, you can do much better. And in fact, immediately the community followed, and our predicted limits were immediately, basically 1 year from our paper, met, and now even exceeded in some cases. So that was, I should say, if you look at these frequencies, so this is the oscillation frequencies again on the order of a year, and this is on the order of a month. So this is relatively low frequencies, okay? And recently the attention has been drawn that the masses actually could be much higher. For instance, in a micro EV range or something like this. And this has motivated looking into a possibility to detect such fast oscillations. And we actually had an idea, and we were so excited about it, we thought we can do it in a weekend. So we call this experiment weekend relaxion. Relaxion is also a type of particle, can be both scalar and pseudoscalar. So we were specifically interested in this. So it's weekend relaxion search laboratory, or RESL experiment was born. Of course, it took not a weekend, but several months, but we set this up. And this diagram may look a little bit complicated, but in fact, anybody working with laser spectroscopy routinely uses these Doppler-free saturation spectroscopy setups to stabilize their laser. And our idea was that if the fundamental constants are changing, then again, the frequency of an atomic transition will be changing. And if we lock our laser frequency to a Fabry-Perot cavity that cannot respond so fast to these oscillations, we should be able to see a jitter in atomic frequency. And so we set up this experiment, and really with minimal effort, we were able to get limits. You can see a few times 10 to minus 15 in relative frequency, all the way up to a frequency of 100 megahertz. And we published this last year. And since then, we have been working on trying to improve it. And this is some preliminary data with much smaller integration time than in the original RESL experiment. And you can see that we already are approaching 10 to minus 17. And I think we are quite optimistic that maybe shortly we will actually break the 10 to minus 18 limit here. And so this is a nice way that we find to look for this type of dark matter. Now, these searches, they bring up some interesting theoretical questions. So this field of variation of fundamental constants is now maybe over 10 or maybe even longer, maybe even older than that. And people have sort of some ingrained notions about this. For instance, we've been taught by our theory colleagues for a long time that it is meaningless to speak about variation of constants that have dimensions. And the reason for this is actually very reasonable. So if you are measuring some object, say with a ruler, the length of some object with a ruler, and you see that it's changing, can you say that the object is changing, or maybe the ruler is changing? So you always need to kind of go back to dimensionless constants, and therefore people look for variation of alpha, fine structure constant, or mass of electron to mass of a proton, or something like this. But this notion has to actually be re-examined if you are looking at oscillations of constants on the time scale that are faster than the reaction times in your apparatus. In this case, you can actually effectively talk about variation of things like, for example, mass of electron, because you can form the needed dimensionless quantity. For instance, you can talk about instantaneous mass of the electron over the time average mass of the electron, and then you don't need any other scale. So it's basically a self-referencing measurement. And so this is discussed in this recent paper for those who are interested. So, okay, just moving on, there are other ongoing experiments, many ongoing experiments that look for dark matter. For instance, I'd like to mention an experiment called GNOME. This is global network of magnetometers of optical magnetometers for exotic physics searches, and it consists of over a dozen of magnetometers all over the world that are actually carefully shielded from environmental magnetic fields, but dark matter would ignore the shields. And if you have in particular some kind of topological dark matter, like domain walls or stars, bosonic stars, for example, that should produce signals that have a particular correlation over these sensors, and it turns out to be a powerful technique to separate this from noise. And this experiment is working quite actively. This was sort of maybe one of the first of this kind of experiments, and then this was followed by networks of atomic clocks and so on. And currently the trend is to have multi-sensor networks, and in particular our GNOME experiment collaborates with other people, like with people at the PTB, and we're also comparing with clocks and so on. All right, since my time is short, I'm moving along. There is another type of network search that's possible using a network of gravimeters. And it turns out that on the Earth, we have several dozen of exquisitely sensitive gravimeter devices. These are called superconducting gravimeters that can measure small g to 1 part in 10 to minus 12, maybe, or something like this in a 1 second measurement. So super sensitive gravimeters. And in some models, you can see this is an elephant that is ghostly elephant that is a hint for dark matter. So in principle, it could be that some of the dark matter could be trapped inside gravitating bodies, for instance, inside the Earth. And if it is a type of dark matter that doesn't interact other than through gravitation, then
Professor Gupta, could you finish in about 5 minutes or so?
Thank you so much, Mr. Chairman. I will. Then, if this kind of a heavy object is sloshing inside the Earth, you can detect it potentially with these gravimeters, and then you can further employ the network of this, as I said, and this is an ongoing line of work now by several groups, and in the future, maybe these superconducting gravimeters will eventually be superseded with atom interferometers. I'd like to mention that not only matter sensors can be used to look for dark matter, but also in principle antimatter. And the Pathfinder, so to say, experiment in this direction published its results last year, and this was a collaboration with the BASE group, which is a CERN-based experiment which traps and analyzes antiprotons. And here, I think this is very significant because we sort of most of the time assume that that dark matter interacts symmetrically with matter and antimatter, but that may not be in fact the case. And there are certain examples of pictures, theoretical pictures, where there is such an asymmetry, and this is sort of a direct probe of these kind of scenarios. Okay, just to mention super briefly this other framework for dark matter that I mentioned before of axion quark nuggets. The greatest champion of this is Ariel Zhitnitsky, one of the founding fathers of the axion theories. So you know that one of the types of QCD axion has this unpronounceable abbreviation, and he is the Z here in his DF as Z. The idea is that in the early universe, there could have been sort of a form of quark or anti-quark matter that quite naturally appears in QCD, which is not nuclei, but what's called a QCD color condensate. And some of these condensate could have survived. The important feature in Zhitnitsky theory that such chunks of this matter are stabilized by the presence of axion domain wall that hold the pressure of this stuff. And these things are really macroscopic. They could be typically 10 to minus 5 centimeter in diameter and carry the baryonic charges of 10 to the 25 or so. And the reason these things could be dark matter is not the weak interaction, but because they have a very, very large mass to cross-section ratio. And in fact, astrophysics apparently constraints is just that, not the interaction strength directly, but the mass to interaction cross-section. And when such a thing hits, for example, the Earth occasionally, then there is very strong interaction if it's made out of anti-quarks, which would be, by the way, the explanation for matter-antimatter asymmetry. Then there is annihilation, and there should be a lot of energy released, and through that energy, in fact, people are currently trying to look for these nuggets. All right, I have no time to tell you any details of that, but just to summarize my talk, I think that various kind of quantum sensors, if you like, this is a popular theme now, quantum sensors, are setting traps for dark matter. So it will be nowhere for dark matter to hide in the near future. And among these, I gave some examples of experiments that obviously I'm myself, I'm quite interested in. This is the network of magnetometers, nuclear magnetic resonance experiments, gravimeter experiments, antimatter experiments, and some kind of atomic clocks or laser spectroscopy experiments. And with that, I believe I am at the end of my presentation, and I thank you for your attention.
Thank you very much, Professor Butker. Now it's time for a few questions. I have here a few questions already. The first question by David Thunderstorm. Do we measure any gravitational effect of dark matter in our solar system?
Yeah, so there are probes of that. But there is no currently any detection. So these are all searches at the moment. But yes, people are looking for these kind of effects.
And I think the second question is also somewhat related to this. Another question by Jasmine Gupta. Does dark matter exist in every galaxy? I think if it did exist, it would be all pervading, right?
Well, so there were some. It's a very interesting question. There were some reports a few years back, just maybe 2 or 3 years back, about observation of galaxies that apparently do not have dark matter. But then I think people have reanalyzed those data, and I think that conclusion has been revised. So I think, as far as I know, all galaxies where one can measure do have dark matter.
Okay. Well, I have a third question from Satyajit Saha. It says, compared to ADMX experiment, which also searches for pseudoscalar dark matter candidates, how will the Casper experiment stand in terms of setting upper limits of axion dark matter scenario?
Yeah. So first of all, Casper is generally looking at lighter dark matter. At the lower frequencies or lighter masses of the underlying particle. And it's very important to realize that Casper is not looking for axion photon coupling as a DMX does, but looking for two other types of coupling. So particularly if you go to the axion-like particles where things are not as restricted as for sort of QCD axions, then these couplings can be different. Technically, we are looking for something different, but at the same time, we are trying to design our experiments to sort of extend the range of masses to connect with a DMX.
Okay. Well, I have no more questions, but we still have a few more minutes to go. So if some of you would like to ask questions, you're most welcome. In the meanwhile, I had a question, perhaps very stupid, I don't know. You're looking for very low frequency effects. I mean, frequencies on the order of several months, years kind of things.
Mm-hmm.
So aren't there, isn't there possibility of external ambient biases to come in?
Absolutely. So I must say that today I told you about frequencies from an inverse year all the way to 100 megahertz. So the Russell experiments, they go up to 100 megahertz. When you go to low frequencies, indeed, it is very important to separate from slow drifts in the apparatus. For instance, magnetic fields are known to drift a lot. So for example, for these types of NMR searches, we have introduced a co-magnetometry technique where we have different transitions with different sensitivity to magnetic field and this gradient interaction. And if you use gradiometry, which is actually a common technique for many precision experiments, especially the EDM experiment, there's always a worry, is your magnetometer exactly collocated with sort of your sensing nuclei or sensing atoms? We solve this problem by having a co-magnetometer within one and the same molecule. So this is sort of similar to what the ACME experiment does for electron EDM, where they use different states in the same molecule, which have different EDM sensitivity. Here, we play the same kind of trick, and when our co-magnetometer is on the same molecule as our sensor, this provides a very powerful way to separate these two effects. But this is a very good question, exactly hitting the heart of the problem for these frequencies. So thank you for it.
Thank you. Thank you very much for that excellent talk, Professor Bhutkar. Now, I think we shall, if there are no more questions, I think we will break at this point for half an hour. So I hand over to Dr. Bindya Arora for perhaps announcements.
Very
Thank
quick
you again.
announcement. The poster presentations are now available, and I am sending the web link to access all these presentations. So I request all the participants, all the speakers to kindly go through these posters and maybe give them likes, that they are going to help us evaluate the top 6 posters who will be invited for a live session. And also the question answers can be asked by directly going to the link on the YouTube for those videos which have been provided in the website itself. So you can ask questions from the audio participants who have been already notified to be active, and answer as many questions as possible. Thank you so much. So here's I think a 30-minute break, coffee break right now, and we shall join again at 4:30.
Okay, thank you, Vindhya. Join again at 4:30.
Yes, thank you. लॉगिन करते हैं, अभी मैं तेरे साथ ऑनलाइन हूँ। रिव्यू में कर रही हूँ ना नीचे, हाँ सबमिट बटन तो दिख रहा है, दिख तो रहा है सर, प्रीव्यू में तो सबमिट बटन दिख रहा है। चल कोई नहीं, मैं देख उसमें कर प्रीव्यू में जा। हाँ तो मेरे को तो यार प्रीव्यू में सबमिट बटन नीचे दिख रहा है। यार नहीं तो ये सिमिलर फॉर्म को एग्जैक्टली दोबारा बना देता है। मैंने बनाया मेरे प्रीव्यू पे तो सबमिट बटन दिख रहा है क्लास में।
Hi, Drake. Nice to see you. After a long time.
Hi, Professor Drake.
India, we have.
Yeah, there. Now I'm unmuted. Yes, good morning. It's great to see you. And thanks for organizing this wonderful meeting. It's really, I missed the past couple of talks because I was asleep, but I was here for the opening.
Okay.
Nice to see you after a long time.
Yes, indeed. Yeah, I very much enjoyed my visit a couple of years ago now.
So we shall start in a few minutes' time, another 2 minutes.
Hi, Per.
Hi.
You.
Look.
Okay, we are ready to start the session back in again. So welcome back, all of you. I'm Amitav Sengupta. I'm chairing this session and conducting the proceedings. So our next speaker, I'm very pleased to welcome Professor Per Johnson, who belongs to Department of Material Science and Applied Mathematics, Malmö University in Sweden. The research interests of Professor Per Johnson are mainly in the areas of quantum structure calculation and program development. He is also interested in analysis of satellite sensor data with applications to climate change technology in mathematics education. The title of the talk today is Atomic Structure Calculations, Applications and Code Development. Professor Johnson, you have 25 minutes of presentation, followed by 5 minutes of discussions and questions and answers. So if you like, I'll give you a gentle reminder at the end of 20 minutes, just to let you know. Okay, thank you. So please go ahead.
Thank you very much. So I will share my screen. Okay, so I will talk about atomic structure calculations, applications, and code development. First of all, I would thank the organizer for inviting me to give this talk. It's very exciting to do this over Zoom, but so far everything is going smooth. So I would like to dedicate this to Professor Bhanu Das with the hope that we can extend our collaboration. We have one paper together on neutrinos, but I hope that this will be followed by more work together. We have an atomic physics group in Malmö. We are both experimentalists and theorists, and we are basically interested in external interactions, nuclear effects, and also astrophysics. We have several postdocs and PhD students. I will have an outline, so I will show you some pictures of Sweden because this is an exotic country, I guess. I will talk about the computational atomic structure group that we call COMPAS. I will talk about astrophysics applications, and then I would talk about some new methods for computing wave functions and expectation values. So Sweden is a country far north. So here it is. And if you look at Sweden, if you go, so we would have one part north of the polar circle. It's very wild nature, extremely beautiful, with basically no people living there at all. We have lots of snow in the winter, and this is actually the thing that I enjoy most, to be outside in the wintertime skiing. It's lots of forest. This could be basically a picture from outside of the village I'm living. So it's forest, forest, forest. And then we have the equivalent of the Indian elephant, that is the moose, the king of our forest. And then we can see this animal from time to time outside. I would give some motivation for atomic structure calculations. There are lots of motivations. There are these more fundamental QED alpha variations, atomic clock. But there is also a tremendous need of atomic data for astrophysics and plasma physics. That goes for both for astrophysics and plasma physics with respect to nuclear fusion. There is also an interest for atomic data for studying the interface between nuclear and atomic physics, combining theoretical atomic data with measurements. Then we can infer something about the nucleus. This is a very active field. There is also a need of atomic data for medical applications. And also here, I think a computational route would be necessary. We are in a group. We have a group called Computational Atomic Structure Group named COMPAS, and we meet very regularly, and then we do work together. And you can recognize Charlotte Fröse-Fischer, who is one of the founders of computational atomic physics. She is standing here. And also for relativistic calculation, it's Professor Ian Grant, one of the pioneers of relativistic calculations. You may recognize Michel Godefroy in Brussels and Gediminas Gaigalas, who's an expert on tensor algebra and computation of angular properties. So this group meet regularly. We have a homepage where you can download publications, codes, etc. The COMPAS group has a specific aim, and that is to provide open source multi-configuration codes for atomic bound state properties. And these codes comes with documentation. Another goal is to improve the computational methodologies to meet the requirements in different applications. We collect and exchange knowledge, and this part is also extremely valuable or important. We educate the new generation of scientists. The working horse for us is the GRASP-2K. It's the general relativistic atomic structure package, and this dates back to the work by both Ian Grant and Charlotte Fischer. And if we look at this relativistic multi-configuration method, basically we have a fully relativistic 4-component Hamiltonian. We base our calculations of the wave function based on this Hamiltonian. And then from the wave functions, all measurable quantities are obtained as expectation values. And the wave functions are expanded in terms of configuration state functions. And the configuration state functions, they are made of products of one electron orbitals, and then you antisymmetrize and then you couple. radial parts of the 1 electron orbitals are numerically defined on a radial grid. And we have more than 50, well, we can choose, but we have at least 50 or more grid points inside of a nuclear volume. So it's possible to probe also this isotope shifts and the nuclear extension of the nucleus. There is a limitation. Orbitals are required to be orthonormal. That can be relaxed, and I will talk about this later. So when we do our calculations, well, typically we have between 90 and 120 orbitals. That depends a little. And the expansion sizes, that could vary between 2 millions and 20 millions. And 20 million, that puts strains on our computational resources. When we do our calculations, we always do them very systematically. We have some rules for forming the configuration state functions from the radial orbital sets. So, and then we increase the set of radial orbitals, and then we monitor the convergence of computed properties. And we relax our rules and monitor the convergence of the computed properties. So we do things in a very systematic way, extending the basis in a well-controlled way. And in this way, we can get some estimates of our uncertainties. If we look at the GRASP-2K package, there are lots of things you can compute with it. So, of course, energy levels, often we are interested in not in one or two levels, but several hundred levels of a spectrum. It includes bright and QED effects. We can compute transition rates, and then we can handle the case where you have different orbital sets for the left-hand side and for the right-hand side, so we can efficiently handle with these non-orthogonal effects. We can compute hyperfine structure and isotope shifts, including the effects of deformed nuclei, etc. Professor Geigele have coded routines for shift moments, EDM, etc. Landé G factors. Then we can have look at an atom in a general magnetic field and see what this will bring about. And then we can compute induced transition from symmetry breaking interactions. So there are lots of different modules. So I will take an application. So this is the sun. So this is the active sun. You have a flare, so plasma going out in the corona. We know that the corona is very hot, several million degrees. We are very proud that this was figured out by Bengt Edlén from my home university, Lund University. And there is an energy transfer from the lower atmosphere, and that is debated, but it involves magnetic fields in some way. Here we have a spectrum. So on this axis we have the wavelength, and this is the number of photons. You have different ranges, soft X-ray, strongest coronal lines, and these are the missions. That is Hinode. There are other missions, space-based missions. The problem is that atomic data for analyzing atomic astrophysical spectra, they are lacking in many cases. Not only are they lacking, but there are very few lab initiatives to take this data or provide this data. And there is an editorial in Nature from 2013 saying that lab spectroscopy has long lagged behind telescope observations, but it's striking just how wide the gap has now grown. That means if we are going to do progress in astrophysics, atomic data to a very large extent has to be calculated, and this is challenging. We have what we call a calculation of spectroscopic accuracy, and spectroscopic accuracy that has to be, well, taken relative to the wavelength range you're observing. So if we observe X-ray, soft X-ray, or EUV region, our goal is to improve our computational methods that we can provide spectroscopic accuracy so that we can compute transition energies as good as they can be measured. And if we can do this, then these computed transition energies can be used to directly aid line identifications in spectra. Otherwise, this has to rely on lab measurements, and these lab measurements are to a large extent lacking. So we aim to compute transition energies as accurately as they can be measured in astrophysical spectra. I will give you an example of this. So this is aluminum-like, so it's the ions around iron that is most interesting. So we do this, we compute both atomic level and the transition probabilities for a large number of ions, but the most interesting ion would be aluminum-like iron. This is a typical calculation, so we aim at a few hundred states. The basis functions expansion, in this case, is around 5 million. And the uncertainties in excitation energies for this ionized system, these are quite low. And that allows us to nail misidentifications and confirm tentative identifications. And also the calculations provide transition rates, and transition rates, this is very difficult to infer experimentally. You can rely on old beamfoil measurements, but this is just for lifetimes. To get transition rates, this is extremely difficult with experimental methods. So we have to rely on calculated atomic data. This is an example. The numbers are uninteresting. It's just to show that for many of these lower lying states, so this is in iron, for many of these low lying states, there are experimental transitions available. And if we compare what our calculations with experiment, you see this is an extremely good agreement. But as we go higher up in the spectrum, less and less experimental data is available, and we use our calculations to either confirm or say that some identifications might be wrong or uncertain. So this is an example. If we look at the level, so this is level 128. This is what we compute, and this is the atomic data available at NIST. This is tentative data by Giulio Del Sana. So he used our computed energies to find the proper lines. And this way of working works very, very fine. So we can either say that some identification might be wrong, and then we can confirm tentative assignments. I will show it's very important to do these calculations in a systematic way. So this is magnesium-like ions. So we have been looking at excitation energies for high-lying states in magnesium-like iron. We can do the lowest order correlation, that would be the valence, and then we can add valence and core valence, and then we can systematically also include core-core. And this is how these calculations typically look like. So on this axis, you have a excitation energy in kilo Kaisers, and this is the calculated minus the observed energies. So you see, if we have some valence calculations, then we, of course, the calculated energies are not very accurate. And then we add valence and covalence, that would be the red ones, a considerably better agreement. And then we add all correlation, valence, covalence, and core, that would be the black. And we can see that we have some outliers, and these outliers could then be identified as experimental problems or assignments that are not correct. So this has been a theme of our research for quite some time, and then we have covered quite a lot of ions, and we are extending this, and we are collaborating with astrophysics, and they provide us with this observed data, and then we look at tentative identifications. Can we do calculations better? Yes, I think we can. So in our multi-configuration calculations, we are limited to an orthogonal basis set. And this is due to the fact that we have to compute the matrix elements. And if you have non-orthogonal orbitals, this is very time consuming. But we have ways to very efficiently compute this matrix element. And if we, instead of having one orthogonal orbital set, if we have many non-orthogonal orbit sets, say one orbital set describing valence correlation, another orbital set describing covalence, a third core, then we can get much faster convergence of the computed properties. And this is the way we want to go, and we have already non-relativistic code and non-relativistic Breit-Pauli code for this. And if we look at an examples what you can do, so this is now not highly charged ions, so this is carbon-2, so it's a 5-electron system. If we want to compute this excitation energy, we can see that using this method we can predict it quite well, not as well as if you use this explicit method like Hüller's type of calculations, but these, on the other hand, they are difficult to extend to more electrons, but we can come very close, and we see that in many cases we get a smooth convergence, making it possible by this new technique, making it possible to extrapolate values. And now, again, looking at the sum.
Johnson, could you try to wind up in about 5 minutes or so?
Yes, I will. Thank you.
Thank you.
So again, looking at the sun, an unanswered questions is how strong are the magnetic fields out here. This can be inferred from magnetically induced transitions. So we have codes to compute wave functions for atoms in external magnetic fields. And if we have external magnetic fields, then we would have J-state mixing due to symmetry with symmetry breaking B field. And this would open new decay channels. So I will give an example. So the plasma physics motivation is to infer strengths of the magnetic fields in plasma from intensity ratio measurements. This is from Astrophysical Journal, and I will go to the system. So this is chlorine-like iron. This is the levels. So here we have a ground configuration, and this we have an excited configuration. And if we look at this J7 half state, we see that this can decay down to the ground configuration only through a very, very weak M2 transition. If we look at this 5 half state, we see that this can decay down to the ground state through a very strong E1 transition. And in an external magnetic field, these two states are mixed. And that means that we would have a magnetically induced transition that we could measure from the 7/2 down to the ground state. So 5/2 and 7/2 are mixed in an external B field, and then this mixing will open a decay channel called magnetically induced transitions. And the mixing of the strength of this transition depends both on the magnetic field and the fine structure separation. And if we look at this fine structure separation, there is a degeneracy. And that means that the 5/2 and 7/2 are extremely close to each other. So there is an accidental degeneration. That means that this magnetically induced transition is strongly enhanced. And also this is a degeneracy for chlorine-like iron, and chlorine-like iron is abundant in the solar corona. So we can see that we have a probe from God. So this is very accidental, and this will enhance this effect. The problem is that this fine structure separation is so small that it's difficult to be measured. There is some measurement here. This is uncertain, but this needs to be determined more accurately. Calculations cannot predict this fine structure very well. There are lots of different methods. They will all give different values, but we need to infer this energy separation experimentally. And these are some simulations. So here you can see this is the charge, and this is iron. And you see that this is the transition rate of this induced transition, and this is the dependent on the external magnetic field in Tesla. And the two different scenarios depend on this experimental field or experimental fine structure separation. So if this can be measured, it can be measured with an EBIT system, then we have a method to measure these magnetic fields. So I will wind up by saying that many calculations there are lots of elements needed for astrophysics. Many of these calculations are extremely challenging. I think in the future we need to have some semi-empirical tuning of these calculations. We need massive parallel computations, MPI, OpenMP, so that we can have large basis sets. But I also think that these systems requires new computational methodologies for us to provide the data the astrophysicists need. So thank you very much.
Thank you, Professor Johnson, for that wonderful talk. I have a few questions here, but before I go to the questions, I'm tempted to add a couple of points to the exoticity of your country that you described earlier. You said your country is very exotic. You have a lot of snow, a lot of forests. But I think you're also exotic because you are the land of the midnight sun.
Yes.
You are the land where the Nobel Prize originates.
Yes, yes.
Okay, so let's go to the questions. Question from Ritvik Srikantam. Has deep learning been used to reduce the time computational complexity in atomic many-body problems?
We haven't used it, but this will be actually when we apply for money from the Swedish Research Council the next time. This will be something that we will look into. I think this is the route that we have to go. And I think there are lots of things to do in this field. So it's very hot, and I think almost important or necessary to do this progress that we want.
Okay, so the next question by Ayaki Sunaga says, which effective QED potentials are implemented in the latest version of GRASP?
Yeah, so the latest version of GRASP varies this module QED mod from the Petersburg group that accounts from the self-energy and also from the vacuum polarization. This is implemented in GRASP. So the QED mod.
Thank you. So there's a second question also from Ayaki Sunaga. It says, for the calculation of Fe atom, if I understand, you use CI method, which is generally less accurate than the coupled cluster method. Why is your calculation so correct?
Yeah, well, so we use CI methods, but you can add these perturbative corrections, and that allows us to have nominally very large CI expansions.
Okay, thank you. So there's a question from Vijaya Sahu. Can you comment whether CI plus MBPT or your method is more reliable? As I see many calculations are performed these days using CI plus MBPT method to produce energy levels of multivalent systems.
I think that the CI plus many-body is a very attractive way of doing these calculations, as the many-body part takes care of correlation very efficiently. I think that this would be also a route that we would like to go, but as for now, we include this often correlation perturbatively. In some way, this is, if not equivalent, it's something like that. But there are many things to develop when it comes to this. But the CI many-body is extremely interesting and attractive.
Okay, I think I'll take one more question. This is from Sir Gordon Drake. Can you say a little about how you calculate the QED corrections and their uncertainty?
So I'm not an expert on the QED corrections, and there are different modules implemented. There is the group of Professor Schwertfeger, but some PhD students have been working with this, and they implement both this QED mod, and then there is some other schemes from I think it's from both Pekka Pykke and let's see. I'm sorry, the name has fallen out from my head, but there are different QED models implemented, and we have been studying this systematically by comparing with data from highly charged tungsten to infer which is the best. This is what I can say for now, but the details I cannot see exactly what difference there is, but it's QED mod and some other models.
Okay, thank you. There's one question from Bindia, but I think I'm going to skip that because she's an organizer. She can get in touch with you directly. There's one final very short question from Kotagiri Ganga Prasad, which says, which programming language is used to develop GRASP 2K code?
So so the latest version is in Fortran 95, but GRASP is a legacy code. So much of the coding was done by Irongrad and the Oxford group using Fortran 77, but the program as a whole is converted to Fortran 95.
Okay, so I'm sorry, I have to leave out a couple of questions, one from Bindia, one from Ben Ohayon. Would you kindly contact Professor Johnson separately? because we really have to move ahead. So once again, thank you very much, Professor Johnson, for that excellent talk, which has generated so much discussion. So now we move on to our next presentation by Professor Gordon Drake, together with Mr. Aaron Bondi. He belongs to the Department of Physics, University of Windsor in Canada. He says Windsor is Canada's one of the southernmost border cities. So the group of Professor Drake, along with his students, developed new tools to probe the properties of atoms and nuclei by combining the high precision theoretical techniques developed in-house with the high precision measurements made possible by the modern methods of laser spectroscopy. The title of the talk today is Atomic Physics Searches for New Physics, Beta Decay of Helium-6. Professor Drake, you have 35 minutes of presentation, followed by 10 minutes of question, answers, and discussions. So if you like, I'll warn you at the end of 30 minutes.
Okay, thank you very much. Share my screen. Let's hope this works. Oh dear. Oh yes, okay. I have to go here and go back to the beginning. Oops. Okay, yes, here's my topic. Thank you very much for the invitation, and good morning from Windsor, Canada. Unlike Sweden, we're in fact a long way south, just about the same latitude as Gibraltar here. This is a joint theoretical experimental collaboration with the University of Washington and the group of Alejandro Garcia. As I'll give the first part of the talk, and then my PhD student Aaron Bondi will take over for the second part.
We are unable to see your screen if in any case you're sharing it. We don't see it.
I'm sorry, you can't see my screen?
No.
So can you see any of my talk?
No, we see you.
Yeah.
Oh, only me. Well, I did do share screen. Let me see what I can do about this. I'm clicking on share screen. Share. So you can't. So have you enabled me?
Yes, it's already enabled.
Well, I'm clicking this little green icon at the bottom of the screen, share screen.
Can you click exactly on the green button which you see for the screen share and not on the left and right? That might not allow you to do. It's exactly on the
share Alt S. See, does that do anything? No, I guess that didn't help. Well, when I click on share screen, it changes the appearance of my screen. So I don't know why it's not coming through.
Dr. Drake?
Yes?
In the bottom right corner, when you hit share screen, the blue share button, I think that's the last thing you have to click.
Oh, share. Oh, yeah, okay. Yeah, can you see it now?
Yes.
Yes. Yes.
Okay, good. Yeah, yeah, it's a wonderful technology, but it's the first time I've actually done a talk this way. So let me continue on then. I'll first talk about some motivation, and then resources. A new edition of the Springer AMO Handbook is coming out. A proposed experiment by Eric Hessels, and then continuing on to our main topic, which is the helium beta decay. And I'll say some introductory remarks about that, and then hand it over to Aaron. Now if I can just get my... so yeah, it's not going on to the... So Aaron, how do I make it go to the next slide?
Yeah, so I think here you'll just drag the PDF down, kind of thing.
Oh,
like in the
see, I wonder
toolbar on the right there.
if I go to
Yeah, if you go full screen mode,
full
that might help.
screen.
Yeah.
Okay, there. Is that better?
Yeah.
Okay, so the main motivation for this is that, and this is the underlying theme for all our talks today, is that high accuracy atomic physics measurements at low energy have the potential to complement or even extend what can be learned from high energy particle experiments. So this is becoming a hot topic, and is the main theme for my talk also. And I just wanted to mention that a new edition of the Atomic, Molecular, and Optical Physics Handbook will be coming out soon. And in fact, it contains several new chapters on searches for new physics, tests of fundamental physics, parity non-conserving effects, atomic clocks and constraints on fundamental constants, searches for new physics, including dark matter, and then several topics covered by Mariana Safranova on searches for new physics. So I hope that this will be a valuable resource for people to learn more about what's going on in this area. I just wanted to mention in passing what I think is a very promising technique that's been proposed by Eric Hessels at York University, just down the road from where we are here in Windsor, to measure the electron-electric dipole moment by trapping a polar molecule such as barium fluoride in a solid argon crystal, trapping it in that way, and then using reversals of all of the available fields, electric fields, to measure the electric dipole moment. And he anticipates that this might allow a 3 to 5 orders of magnitude improvement. So this is under active development at York University. For our main topic, as you can see down here at the bottom, is the beta decay of the halo nucleus helium-6 into to form lithium plus the beta particle and an antineutrino, and the main experimental measurement is the angular correlation between the beta particle and the antineutrino. This is a review article, a very useful one, just appeared by Gonzalez Alonso, Naviliat Kuncic, and Severian. The main effect comes from this term indicated by the red arrow, involving the momenta of the beta particle and the antineutrino. So here's the correlation term, which allows you to determine this parameter alpha, which gives enables you to determine it's predominantly a gamma of Teller transition, and X here is the Fermi fraction, and the signal for new physics would be indicated by a deviation of this correlation parameter, depending on whether there's an additional tensor component to the interaction, and that would produce a change in the ion recoil momentum, as indicated at the bottom of the slide here. There are other experiments going on with this. First, our collaboration with the group at Washington State University. This will be one paper that Aaron will refer to, and then our own theoretical paper from 2015 at the bottom of the slide. There are other experiments in progress, one at the Weizmann Institute. This is just referring to the case of helium-6, and also at Ganil, we'll be referring to work at Ganil with their LPC trap and some theoretical work for helium plus. So the main issue is that is what happens to the lithium-6 ion that's formed. If we start with the the one electron case of helium-6, in this case, you can form either lithium-2 plus or lithium-3 plus. If it's just one electron. And here there's perfect agreement between theory and experiment for the fraction of lithium-3 plus formed. But if you look at the 2 electron case where you start with helium, neutral helium instead of helium plus, then there's a disagreement between theory and experiment, as shown by the table here at the bottom, a 2 order of magnitude disagreement between the fraction of lithium-3 plus. So this is the main issue that we're trying to address. And so I'll now turn it over to Aaron to talk about his work on addressing this problem of resolving this discrepancy between theory and experiment. So Aaron, can you take it from here?
Yeah, so you just have to stop sharing and then I'll be able to start.
Okay, so how do I do that? Let's see.
At the top of the screen.
Oh, stop share. Yeah, okay, there we go.
Okay, so can everyone see my slides right now, presumably?
Yes.
Okay. So yeah, I'm Aaron Bondi, a PhD student of Professor Drake's from the University of Windsor. And I'm very happy to be with all of you today and wishing everybody good health during the pandemic. And a big thank you to the conference organizers for putting this on. So yeah, I'm excited to talk to you today about minus decay of helium, some work that we've done side of this aforementioned collaboration. So, so we're ultimately looking for new physics, big spirit of this conference, beyond the standard model, in the umbrella of probing the weak interaction. And for us, what that means is study of the beta minus decay of helium-6. So this beta decay has an equation looking like this, where a helium-6 atom, after undergoing beta decay, forms a lithium plus daughter ion, along with the leptonic pair, the electron, otherwise known as the beta particle, and the corresponding antineutrino. And as mentioned by Professor Drake, the helium-6 atom has a halo nucleus, and I just wanted to show what this looks like. So in this atom, this isotope of helium, the 2 extra neutrons sit outside of what was previously the nuclear structure of helium-4 and kind of surround it like a halo. And basically due to the imbalance between protons and neutrons in this isotope, it's ultimately unstable and has a lifetime of about 0.8 seconds. And this makes it a good candidate to work with for beta decay because it lives long enough to be manipulated, but it's still decaying enough to do good experiments on it. So we consider one of these helium-6 atoms inside of the experimental apparatus, the trap, which I'll say more about in a few slides. After its lifetime, it undergoes a beta decay event, leaving the following kinematic structure. So here in the center, the helium-6 atom has undergone decay, and as products, we have the lithium-6 daughter ion, along with the leptonic pair, which consists of the beta particle and the antineutrino. And highlighted here is angle theta, because this is, as Professor Drake mentioned, the experimental quantity of interest. And it's ultimately related to W here, the angular distribution of the beta particle by this dot product of the momenta, which brings in angle theta. and it is ultimately the electron antineutrino correlation coefficient A here, which we seek to find potential deviations in this value from the predicted -1/3 by the fact that it's a Gamow-Teller process under the standard model. So what makes this decay challenging experimentally is that the antineutrino here cannot be detected in the experiment. And as such, we need to use conservation of energy and momentum and knowledge about all the other constituents of the process in order to determine angle theta. So this includes knowing the energy and momentum of the initial helium-6 atom, and likewise for the beta particle, and also the recoiling 6 daughter ion. However, for this recoiling daughter ion, a few different atomic processes could take place. So the first would be that it remains as lithium plus in what is called a shake-up process, where there's just an excitation of an atomic electron. But what could also happen is shake-off processes, wherein either 1 or 2 electrons are ejected, forming lithium double plus or lithium triple plus, respectively. Now, if this happens, since we're concerned with conservation of momentum, we need to consider what happens to these atomic electrons, as they could carry away additional momentum that really needs to be accounted for if we expect to get a precise value for theta, which we definitely need in this probe for new physics. So now, just to show the actual experiment and describe a little bit about how this takes place, our experimental colleagues are from the University of Washington in Seattle, and it's the group of Alejandro Garcia, as mentioned, and these figures here come from this 2017 paper of Hong et al. That is our most recent collaboration with them on this particular beta decay. So on the left here is the apparatus, the chamber where the decay events are actually measured, and on the right are time of flight analyses that I'll talk about shortly. So what happens in the experiment is the atomic beam is sent into this column here. And so first of all, the atomic beam is formed. We get the helium-6 by bombarding a lithium-7 target with an 18 mega electron volt deuteron beam. And this is done with the Van de Graaff machine at SEMPA at University of Washington. And the helium-6 atom is a product of this nuclear reaction. So once we have that in hand, it is down into the column, most ground state, and is selectively excited to the metastable triplet state. And then eventually a magneto-optical trap is formed using 1083 nanometer laser light, which is locked to the triplet S1 to triplet P2 resonance. And this laser is selectively turned on and off. So there are some times where the trap is composed entirely of triplet S atoms, and other times where it is an admixture of S and P, which is good because we have also done work on the triplet P state that I'm not going to really get into today, but it reveals interesting angular anisotropy in the results that could be used to understand this experiment in the future. But coming back to the atom in the trap here, so when a decay event happens, the beta particle is going to go up to the beta telescope, and the recoiling daughter ion will be pushed down by this electric field into the recoil ion detector, and that's how each of these is measured. So the beta telescope consists of both a scintillator, which is used to measure the energy of the beta particle, and then also a multi-wire proportional chamber that can be used to track the position in which it enters, which is important for reconstructing its initial momentum. And also this piece of apparatus acts to suppress the background gamma radiation for better statistics. And the recoil ion detector at the bottom is formed with multi-channel plates, and it has good resolution as far as its ability to determine where the beta particle came from, or sorry, where the recoiling daughter ion came from. So once we look in the recoil ion detector, this brings me to these graphs here on the right. And for both of them, on the y-axis, we have the energy of the beta particle. And then on the x-axis is the time of flight of the recoiling daughter ion. Now, the bottom graph is just a Monte Carlo simulation that was performed assuming that there was an equal probability for all three daughter ions, so 33% chance of each. And the top one is what actually happens in experiment. So these dotted lines here, the first one represents the possible, locations in this graph where we could find counts for lithium triple plus. And then the next bigger dotted line is for lithium double plus, and the solid line is for lithium plus. So obviously the lithium triple plus would reach the detector faster because it has more charge. So, and in doing the analysis, you have to apply a beta threshold, which is shown by these horizontal dotted lines. So we have to look at decays that produce beta particles above a certain energy, because above those energies, it allows, there's no overlapping time of flight. So you could unambiguously resolve the particles and their charge state. So you can see here, the last thing I want to say on this one is just there's hardly any counts in the lithium triple plus bin. And as you'll see, this is where we form the stark disagreement with experiment. So, coming back to our motivation, so we're studying for new physics by looking for the beta antineutrino correlation coefficient that I mentioned. And what we've said already too is the big disagreement that we have is on the formation of lithium triple plus following this decay. So we've performed some analysis that brings the results closer, but they're not yet in agreement. So this energy level diagram on the right here for the recoiling lithium plus daughter ion, all the bound states are from negative infinity to minus 4.5, and then the single ionization continuum goes from negative 4.5 to 0. And both of these energy bins uniquely correspond to what charge state we have, where down here it's lithium plus, and from minus 4.5 to 0, it's lithium double plus. However, above 0, we have two overlapping continua, both the single ionization continuum, which continues above 0 because it's possible for one of the electrons to carry away a lot of energy and the other one to remain bound. And then we also have the double ionization continuum with both electrons being ejected starting at E is equal to 0. So the fact that these two continua are overlapping is what we seek to resolve in this work. And so the method that we use begins with the sudden approximation, where we take the nuclear charge going from Z equals 2 of helium to Z equals 3 of lithium instantaneously at the moment of decay. And this has been an approach that has been widely used in the literature and was shown to be just a 1% correction in the related beta decay of the 1 electron helium plus. So by using the sudden approximation, it allows us to expand our initial state in a complete basis set of final states. And the initial states that we consider in this work are the ground state, along with the metastable singlet and triplet states. But it is only the metastable triplet state and the ground state that are actually, they have experimental data to compare to. So we just did the metastable singlet state for completeness. And our final state is a whole pseudo spectrum of all possible lithium plus states. And the e to the ik operator in the front generates the transformation to the moving frame of reference since we're concerned with recoil. Now, we only take the leading term of this e to the IKR expansion, which is 1. And the reason for this, although the recoil effects, which are related to K, the momentum of the recoiling ion, they're very important and totally critical to the overall goal. But particularly for the subset of the project looking at the lithium triple plus probability, we've shown in previous work that this is a very small effect. And so in this particular part of the project, we don't consider that. And I just want to say a little bit about our wave functions. So if you look at the graph on the right here, we have the nucleus placed at the origin, and then the electronic coordinates and the interelectronic coordinate. So when we want to solve the Hamiltonian for the 2-electron system for arbitrary Z, we're using Hiller's wave functions. And the main benefit of Hiller's wave functions is that they explicitly contain the interelectron coordinate R12, and as such represent a fully correlated basis set automatically. So, and then the Peckeris shell, which will appear later in some of my results, is just a measure of how large the basis sets are that we used in the work that we do. The larger the basis set is, the better, and we look for convergence as the basis set is increasing in size. So the transition probabilities that we're concerned with, coming back to our previous wave functions, are just these ones A, which do not explicitly contain K, but as I said, in the overall scope of the project, we are interested in K because it describes the recoil. So with the theoretical method in place, it's very important for us to have checks that we can use to make sure that everything is consistent with known relationships. So the first of these is that we look for complete of the wave function by doing probability closure. And we're able to do this, and I'll show this shortly. And then the second and independent check that we have is a newly derived Cocoon oscillator strength sum rule that is it kind of overarches the work, and it should find use in many other settings. So when you have your typical recoil oscillator strength, as shown here in the first line, the energy difference that you're concerned with typically corresponds to energies from the same Hamiltonian. However, in our system, it doesn't, because we start off with a potential that corresponds to helium, and we end with one that corresponds to lithium. So when we go to formulate the corresponding sum rule, there's this additional term that arises due to the difference in the potentials of the two Hamiltonians. And it brings an extra term into play such that the oscillator strength sum rule is no longer equal to 2, the number of the electrons, but actually contains an additional term. And this additional term we've shown for all the states we work with, but here is for the ground state to the pseudo spectrum of P states, show that it's well satisfied in general. So I'm going to discuss some previous results for the formation of the daughter ions. And in the top here, I'm showing the ground state. And in the bottom table is the metastable triplet state, where each row is separated by the respective charge state of the daughter ion. So the reference 1 is the reference that Professor Drake mentioned from 2015 that our group did on this problem. And then reference 2 is a B-spline approach used by Wouters and Vec, another theory approach. And then the first experiment that we compare to for the ground state is this 1963 work by Johnson et al., which is a classic work in the early years of trying to study beta decay leading up to the electroweak theory and then the standard model, understanding what the nature of beta decay was. And then reference 4 is our current experimental colleagues whose apparatus I showed on a previous slide. So for all of the lithium plus and lithium double plus, we see that there's pretty nice agreement. It's not perfect, but they're pretty close across the board for both states. However, for lithium triple plus, the same can definitely not be said. Compared to the 2015 results, there's about 2 orders of magnitude of difference. And so this is what we need to resolve. So the reason that we propose for this is that both of the single and double ionization continuum are overlapping. Now, the B-spline number for the lithium triple plus probability does look about an order of magnitude better than ours, still nowhere close to experiment, but because their probability closure was lost, in moving forward, what we seek to do is use our results and then just apply a method that will allow us to disentangle these two continua. So visually, what we seek to do is go from our previous situation where when we were partitioning based on energy bins, which left us...
Would you like to take another few minutes to wind up? About 5 minutes?
Yeah, 5 minutes is good, yeah.
Okay.
Okay. So we were using energy bins to partition here, where that left us with 2 overlapping continua in the E is greater than 0 region. And what we need to do is actually partition based on charge state, where everything is uniquely separated. So to do this, the first step that we do is form 1 electron wave functions that can match the outgoing boundary conditions. And for 1 electron wave functions, this is pretty simple because if the energy is greater than 0, then we have a scattering state, whereas if it's less than 0, we have a bound state. And then taking these 1 electron wave functions, we form provably complete product states where we've taken the electron interaction R12 as a small perturbation. And we can show that this is a small effect. So using these product states, we form projection operators that are explicitly composed of product states that correspond to doubly ionized outgoing boundary conditions. And this allows us to apply the projection operator to the previous region that was overlapping with both continua, leaving just the double lithium triple plus continua left over. So for our results, the previous result was 1.2% for the ground state, and that corresponded to the overlapping continua. And here's our new results where they all correspond to double ionization. And in the top entry of each column is the 0th order result. And then in the bottom is the 2nd order corrections. And so we've studied this with increasing basis size in both directions. And as you can see, the results are about an order of magnitude smaller. And the 2nd order corrections themselves are about 2 to 3 orders of magnitude smaller than the 0th order, which provides confidence in the method we used in forming the product states in the first place. So here are the corresponding results for the metastable triplet state, which began previously with a probability of 1.86%. And like the results for the ground state, we've brought the probability down by roughly an order of magnitude. And we can make similar claims about the 2nd order corrections being smaller than the 0th order corrections by 2 to 3 orders of magnitude. So just for completeness, we also looked at the metastable singlet state, where there's no experimenter theory yet to compare to. And we find a similar pattern in the results in that the 2nd order corrections are 2 to 3 orders of magnitude smaller. So just to put everything together, for the initial state of the ground state, we brought a previous number of 1.2% for the formation of lithium triple plus down to 0.32%, which is an order of magnitude closer to experiment, but still an order of magnitude to go. And similarly, for the metastable triplet state, we brought 1.86% down roughly an order of magnitude, and still at least an order of magnitude to go. So we definitely have made progress, but there still is certainly more work to do. And for our next steps, we would like to begin by correcting for the sudden approximation. And to do this, we propose to model the beta particle explicitly in the time-dependent Schrodinger equation and see what effect it might have on the atomic electrons and the transition probabilities. So I'd like to thank you very much for your attention and be happy to answer any questions.
Well, thank you very much, Mr. Pondi and Professor Drake. I have a couple of questions on the chat box here. Let me take the first one. This is a question by Sandeep Dubey. How stable is that strange structure of 6 helium?
Well, it undergoes a beta decay after 0.8 seconds. I don't know if that answers the question.
I didn't really get the question. What was the question?
How stable is that?
How stable
is that strange structure of helium-6? I thought you've already answered it. You said the lifetime is about 0.8 seconds.
Yeah, 0.8 seconds. Yeah, it undergoes beta decay. It's a halo structure and with a beta decay after about 0.8 seconds.
Yeah, I mean, I think that reasonably well answers this question. Okay, so the next question is on theoretical calculations by Professor Vijay Sahu. He says, is there any advantage of considering lighter nuclei for studying beta decay process? Another related question is, what are the roles of QED effects in beta decay, which I presume you have neglected in your calculations?
Yeah, so for the first one, there is, I guess the advantage of studying the light nuclei would be just in general, like, I guess like hydrogen, is an atom that a lot of exact work can be done on. And then helium, we can do quite good. And then past that, it's hard to do, super good atomic theory for these comparisons. So it's kind of a nice middle ground between experiment and theory. And obviously it being neutral makes it nice to work with experimentally, not super related to it being a light nuclei, but I mean, there are a lot of interesting beta decays in heavier nuclei though that, if it were possible to do this kind of theory on it, it would be very interesting because, there's kind of exciting prospects there. But and then for the second question, I guess the if the quantum electrodynamic corrections would be definitely too small to influence.
Yeah, they're too small at this level of accuracy.
Yeah.
Okay. Then the next question from Ben O'Hine is, do you find an energy dependency on the charge fraction? This will affect the recoil ion energy spectrum. This question is probably visible to you too.
Yeah. So the charge fraction, like right now, I mean, so for the energy of
we see it rising from threshold. I think that the question is, how does it behave as a function of energy? And we can get some information on how it rises from threshold, goes to a maximum, and then drops off again.
Okay. Shall we go to the next question? This one from Srinivasa Prasanna. Just out of curiosity, how good or bad is helium-8, another isotope, instead of a heavier nucleus in comparison to helium-6 for this type of study?
I
Well,
mean,
its lifetime is very much shorter. It's at the level of milliseconds. And so that would make it experimentally much more difficult.
Okay, good. So I have yet another question. This is from Ayaki Sunaga. It's a beginner's question, it says. What is the continuum of single plus double ionization? I suppose that the spectrum of ionization is discrete.
Yeah, I didn't get the first part of the question.
What is the continuum of single plus double ionization? And then it says, I suppose that the spectra of ionization is discrete.
yeah, well, it's like I mean, it's ultimately, I mean, in reality, it's not discrete, I don't think, but because like it could go into any continuum state, right? There's
Yeah, I didn't really understand the question.
Yeah,
I mean, I understood the words, but I didn't understand the point of the question.
Yeah, I didn't too, because I think the ionization spectrum is always a continuum. How can it be discrete?
Oh, well, yes, but yes, the neutrino emits over a continuous range of energies. Indeed, yeah, from all the way down to zero, you know, from zero up to a maximum.
Right. Okay. I don't know if this question is answered, but anyway, I think we'll move on because there are no more questions. So once again, thank you, Professor Drake and Mr. Bondi, for that wonderful lecture. Thank you again. So you may unshare your screen, and we'll move on now to the last talk of this session. This is by Dr. Nicholas Hutzler from California Institute of Technology, Caltech, Pasadena, California. Dr. Hutzler's lab at Caltech uses lasers to control atoms and molecules for tabletop experiments in fundamental nuclear and particle physics by using and developing techniques that also have applications to quantum information, computation, and many-body systems. The talk today by Dr. Hutzler is searching for new fundamental physics with polyatomic molecules. Is Dr. Hutzler in yet? Bindia? Yeah, there he is. Okay. So welcome, Dr. Hutzler. You have 35 minutes of presentation followed by 10 minutes of discussion. If you like, I'll give you a gentle reminder at the end of 30 minutes from now. Thank you.
That'd be great. Thank you. Okay. Can everyone see my slide?
Your volume is rather low. Could you?
Is this
This is better. This is better than before, but could it go up a notch higher?
Let me see. Oops.
Well, if not, this will probably do if you speak a little louder.
Okay. Well, hopefully everyone can hear me okay.
Yeah, we can hear you.
Great. Excellent. All right. Well, thanks again for the invitation to come speak, and thanks for coming to my talk. I'll be telling you about some of the research we're doing at Caltech, searching for new fundamental physics with polyatomic molecules. Our broader motivation is the fact that the universe is made out of matter. There's no free antimatter anywhere in the universe. And that poses a problem because all known physical laws treat them more or less equally. So this motivates the search for fundamental symmetry violating physics beyond the standard model. Although this is not the only motivation, this is just one of the big pieces of motivation to search for these symmetry violations. These symmetry violating new physics creates symmetry violating observables at low energies. It also creates them at high energies. So there are a lot of high energy searches for these CP violating physics, particles, and forces. But it also creates observables at low energies, and that's what I'm interested in with my research. So the classic example is permanent electric dipole moments, or EDMs, the very existence of which requires this CP violating physics and would arise from, at least in the type of systems that I'll be talking about, from beyond standard model sources. And not just EDMs. EDMs are the classic example. There are other electromagnetic moments and interactions as well that I will be talking about. The system that I focus on is molecules. These CP violating effects are amplified by molecular internal fields. So the electric field, for example, inside a heavy polar molecule is around 1 million times larger than any electric field that you can create in the lab in a reasonably large volume. And the idea then is that if the constituents of the molecule, just the things that make up the molecule, like the electrons or the nuclei, if they have CP violating moments, for example, EDMs, these will interact with these internal fields and give you energy shifts. Importantly, they're symmetry violating energy shifts. So they're distinguishable from just regular molecular structure backgrounds. So far, molecular EDM searches have focused mostly on the electron. So the ACME experiment with thorium oxide, the experiment at JILA with hafnium fluoride ions, and the Imperial College experiment with ytterbium fluoride. Those 3 molecules have all been used to set an electron EDM limit more sensitive than any atom. And the results are all fairly recent, within the last decade. But there are other molecular experiments, including some that I'll talk about, that are underway, and of course many CP violating EDM type searches in many other systems beyond molecules: atoms, solids, nuclei, nucleons, neutrinos. So it's a big field, and there are several other talks at this workshop. So I said that we were looking for beyond standard model effects with these, just because the standard model would not give, for example, an electron EDM within something like 6 or 7 orders of magnitude of the current limit. But we expect beyond standard model sources to start showing up in the ranges that are currently being probed. This is a plot from a review paper showing what are the particle mass limits for some particular type of supersymmetric standard model extension that we get from different experiments. So EDM experiments, but also direct searches like the LHC, flavor violation, dark matter considerations, etc. And there are a few things to take away from this plot. One is these mass limits are pretty high. You can see that these limits that come from EDM experiments, electron EDM experiment, but also neutron and mercury EDM experiments, are already probing the sort of several to 10 TeV scale for supersymmetric particles. So for motivated extensions of the standard model. Another thing to take away is that if you look at this this entire chart, you see that there are regions where the most sensitive limits come from other sources, like from the LHC or from flavor violation, etc. So there are a lot of tools that we can use with very different experiments to try to probe this new physics. So all these approaches are very complementary to each other. This shading that I've added shows progress since the paper was written. So you can see there's been progress in sort of the masses for every particle for this extension. So it's a very active and exciting field. But For the rest of the talk, I'll focus on CP violation searches with molecules because that's what I work on. One of the exciting things about these precision measurement, the AMO precision measurement approaches, but in particular molecules, is that there's tremendous room for improvement, orders of magnitude of improvement with using techniques and technologies that have been demonstrated in some preliminary form, perhaps. So as an example, a motivating example, let's say that we were able to combine ultra cold trapping quantum control technologies like people do currently with atoms and starting now with some molecules. If we could trap 1 million molecules and keep them coherent for 10 seconds and use some heavy polar molecule that was very sensitive to new physics and with a lot of robust systematic error rejection, and we averaged for 1 week, we would be probing new physics scales of around 1,000 TeV. So that's extremely large. That's far beyond even conceivable direct searches like accelerators. And the exciting thing is that none of these numbers on its own is insane. Each of these has been achieved or almost achieved in some fairly similar system. So no one has done this experiment yet, and this experiment would be very hard. But because of the advances in quantum science, something like this is very realistic now. And so the first step, though, at least if you want to do this, this isn't the only approach, like I've said, but if you want to do this experiment where you have this sort of large number of ultra cold and trapped neutral molecules doing this search, the first step basically has to be laser cooling. So laser cooling, at least in the ultra cold atom and molecule world for most species, is the first step to getting to ultra cold temperatures so you can get these long coherence times in traps. And laser cooling molecules is hard. It's hard for many reasons. I'll refer you to this recent review if you want to learn some more details. But the big problem with laser cooling molecules, the most significant difficulty is that vibrational levels are excited by spontaneous decay. So normally in laser cooling, you scatter a large number of photons to apply forces, including dissipative forces, to atoms and molecules. But in a molecule, if you excite to some vibrational state, for example, the ground vibrational state in some excited electronic state, there's a probability that when that state decays, it will end up in a different vibrational state. Vibrational state decays are not governed by selection rules. They're governed by wave function overlaps. And these wave functions in these two different electronic states, the vibrational wave functions, always overlap a little bit. So if you want to have a successful laser cooling molecule, laser cooling experiment, you have to find one where the electrons are decoupled from the vibrations. So meaning you excite the electron, the vibrational degree of freedom doesn't really care. When that happens, you can find molecules that are that have a low probability of these off-diagonal excitations. So for example, strontium fluoride, which was the first molecule that was laser cooled and laser cooled and trapped. If you excite this main transition between the vibrational ground states into electronic states, there's only around 2% chance that it will go to an excited state, vibrationally excited state when it decays. So, and at 1.6% of the time, it goes to the first vibrational excited state, and then it drops off very quickly, going to higher and higher states. So repumping a molecule like this, closing these leakage channels with additional lasers, is realistic. The type of electronic structure that you want for laser cooling is one where I said the electronic degrees of freedom are decoupled from the vibrational mechanical degrees of freedom. One way to achieve this, not the only way, is to take a molecule with a single metal-centered s electron. So for example, if you take an alkaline earth atom, which has 2 s valence electrons, and you make a single bond to something like a halogen, something that takes one of the electrons away, makes a strong ionic bond, leaves one electron sitting at the metal. It turns out that you frequently get hybridization. When you make the bond, you mix in some excited p state character, and that results in an electronic wave function, which is actually pushed away from the chemical bond. So that's how you can get this decoupling. And what's interesting about this is that this doesn't have to be fluorine. It can be something bigger. It can be something with multiple atoms, as long as it takes this one electron away from the metal, leaving just one electron at the metal. So for example, strontium fluoride was the first diatomic molecule laser cooled. Strontium hydroxide was the first polyatomic molecule that was laser cooled several years later, because OH behaves very much like fluorine when it bonds to strontium. So everything I've said about laser cooling diatomics is largely applicable for suitably chosen polyatomics as well. And what's good news about this electronic structure for CP violation searches is that you also tend to get good CP violation sensitivity with this electronic structure. You have these core penetrating S electrons, which you need for these searches to get, you get nuclear core penetration of the electronic wave function, you get relativistic enhancements, which scale roughly as Z cubed. So you get these large enhancements in heavy molecules with this electronic structure as well. So that's great, and means we can find a number of laser coolable molecules that also have sensitive to CP violation. So fluorides of barium, mercury, radium, thallium, ytterbium are examples. There are more examples. Several of these experiments are being actively pursued. There's a talk in 24 hours by Professor Garcia Ruiz, where he'll talk about radium fluoride. And just as a side note, Professor Das has examined theoretically all of these molecules, and these types of theory calculations to let us know, what molecules are sensitive and how sensitive are they to these effects. Those are really important to help guide the experiments. So Professor Das has had a big impact on this field by helping us learn which of these molecules are promising to pursue. And like the case for laser cooling, this electronic structure giving good sensitivity, that also holds for polyatomics. But I haven't said why you'd want to bother using a polyatomic. And there are a couple reasons. A big one, at least what I'll talk about now, is that there are important systematic effects that you can suppress using a polyatomic. The polyatomic structure of molecules also give you some advantages that are completely decoupled from laser cooling, and I'll talk about some of those later as well. But for now, I'll keep talking about laser cooling. The Acme and Gilla EDM experiments rely on the ability to fully polarize the molecule to do a robust measurement. This is called an internal comagnetometer because you have access to two states with opposite shifts that you can access without flipping laboratory fields. The way you do that is if you can fully polarize the molecule, you can operate the experiment in two states where the molecule is fully aligned or anti-aligned to the lab field. But since the energy shifts are coming from the internal fields, which reverse when the molecule flips direction, these have, for example, opposite EDM shifts. So you can look for this effect without reversing external fields, and external fields are basically the biggest source of systematic effects for these experiments. You also get the bonus that, at least in the types of molecules that I'll talk about, when you fully polarize them, you generally need smaller fields. These diatomic molecules, or molecules in general, that can be fully polarized, you rely on a particular structural feature called a parity doublet. So the existence of closely spaced states of opposite parity that you can fully mix and polarize in these small fields. So for example, in a molecule, you're looking for structures where each rotational state is split into a doublet of two opposite parity states with a relatively small splitting between them. And this is a challenge in diatomics, because in diatomics, this structure can only arise from electronic orbital angular momentum. So the electronic orbital angular momentum in the molecule of the valence electron can interact with the rotation of the molecule through a Coriolis effect, and that's what gives you this splitting. And that's a problem. Well, first of all, this structure is just hard to find. Most things, because of Hund's rules, have no orbital angular momentum in their ground state. But there's a particular problem, which is that it's at odds with laser cooling. So earlier I said these laser coolable molecules have just valence s electrons. They don't have orbital angular momentum. So these molecules I listed earlier won't have these parity doublets. So you can't do this internal comagnetometer trick, at least the way I've talked about. And you need much larger fields to polarize them. These parity doublets, there are actually a lot of neat applications of these parity doublets and things beyond CP violation searches, but I won't talk about those here. Polyatomic molecules, on the other hand, generically have these parity doublets. As long as the molecule has 3 or more atoms, it will have symmetry lowering mechanical modes that result in doubling. So for example, a molecule in a bending motion can have states where the middle nucleus is orbiting around in 2 different directions, or a symmetric top molecule has rigid body rotations around its symmetry axis. And these have these sort of Coriolis type couplings that result in doublings generically, so independent of the electronic structure of the atom, the heavy atom. And that makes these parity doublets available for any atomic species. So neutrals and ions, and for some, like radium or barium, where they just have valence s electrons, this is sort of the only way that you could get this structure. So now I'll talk about some of the things we're currently working on. One good example of this polyatomic structure is YbOH. So ytterbium is similar to an alkaline earth. It has 2 valence s electrons, and it can be laser cooled, and it has broad physics reach via multiple stable isotopes. So it has a number of different nuclear spins. So you can choose different isotopes of this atom and look for electron EDM, shift moment, antipole moment, nuclear magnetic quadrupole moment, etc. And because ytterbium is fairly heavy, you get good sensitivity to all these effects. One effect you can search for with this molecule is a nuclear magnetic quadrupole moment. Like a permanent electric dipole moment, this violates CP symmetry. The very existence violates CP symmetry, and it's also enhanced in molecules because of the large fields and gradients present. So the broader motivation and the techniques that you would use are fairly similar to the electron EDM. But a big difference is that this would arise from completely different physics sources. So this would arise from hadronic sources, things that couple to the nucleus and things in the nucleus. For example, nucleon EDMs, quark EDMs, chromo EDMs, new CP violating strong forces, the strong force CP violation, etc. And if you use a quadrupole deformed nucleus, it turns out you get a large enhancement, typically around an order of magnitude of these effects, because you get collective participation in these CP violating effects, as opposed to with a spherical nucleus, only the valence nucleons really contribute. In these deformed nuclei, a very large number of the nucleons contribute. So you get this roughly order of magnitude enhancement in sensitivity. So this is something that we're pursuing at Caltech. So we're building an experiment to search for a nuclear magnetic quadrupole moment in the 173 ytterbium hydroxide isotope log. It's a spinful nucleus. It's large enough to support a quadrupole moment, and it has a large quadrupole deformation as well. The first generation of this will be a beam experiment. So we'll shoot a cryogenic molecular beam through some detector, look for CP violating spin precession that's also correlated with hyperfine state to look for this nuclear magnetic quadrupole moment. And in the future, we can think of building in upgrades with laser cooling and trapping. For the laser cooling and trapping approach, we're pursuing an electron EDM search. This is a collaborative experiment with John Doyle at Harvard, Tim Stanley at Arizona State, and Amar Vutha at Toronto. For this experiment, we're using a spinless isotope of ytterbium. This makes the structure simpler, makes it easier to laser cool. And in an electron EDM search, this heavy nuclear spin doesn't help you at all. So in this experiment, we want to start using the advantages of this laser cooling and ultra cold temperatures right away. So with these molecules, you always want more of them. So one of the things that we were working on recently was coming up with ways to create more of these molecules in our cryogenic source. The way we make them right now is we ablate a mixture of ytterbium, atomic ytterbium metal powder, and ytterbium trihydroxide, which is some chemically stable powder that you can buy. We mix these together. We put it in a cryogenic apparatus. We vaporize it with a pulsed laser. So when that happens, and this happens in an environment filled with cryogenic helium gas, so we get cold YBOH molecules. And what we do then is we excite the residual ytterbium. There's a lot of ytterbium just created in this ablation process as well. We excite it to a metastable electronic state, which is very chemically reactive. So that state reacts with other ablation products to create more YBOH molecules. We typically get around a factor of 10 enhancement or so. So here's just a comparison of the signals without and with this sort of optical chemical enhancement. And we have some ideas to maybe get more because there's still a lot of unreacted ytterbium in our source. This is also a fairly general method, so it's not unique to this species. So this could be used to create brighter beams of many different species. So this, by exciting to this metastable electronic state in ytterbium, we give this system enough energy to overcome the barriers that prevent it from, for example, from atomic ytterbium turning into YBOH by taking the OH off of something else. It's a chemical reaction, so there's sort of large energy scales involved, thousands of Kelvin worth of energy, but it's dissipated in the cryogenic gas. This is happening still in this 4 Kelvin helium environment. So that energy is rapidly dissipated, and we end up with basically just a brighter cold beam. So the rotational and translational degrees of freedom rapidly thermalize, so we just get a rotationally, translationally cold beam with more molecules. Vibration does not, interestingly. This is sort of a known effect. Vibration changing cross sections through collisions with something like helium are generally very low. But as I'll mention, this is actually very useful for us because it puts population in excited vibrational states that we want to study and that would be sort of hard to get population in otherwise. And this effect works for both the EDM and MQM isotopologues, so we can use this trick in both of our experiments to get more molecules. Currently, we're doing spectroscopy on a few different things. One is the science state. So we want to study this science state, the state where we will actually do the measurement. This chemical production method, like I said, it puts population in these states. So we have populated and observed the science state, but now we want to move on to doing precise spectroscopy, so mapping out all of the levels and all of the molecular constants. So right now, the thing that we're currently studying in the lab is we're actually studying this. So this is the transition that we were initially studying. We're currently studying this transition between this fully characterized state and this state which we want to characterize, so that we can then fully characterize this transition as a way to fully map out not just the science state, but also pathways to populate it and read it out. our lab is partially reopened, so we are actually working on this, although with a reduced staff in the lab. Another thing that we're working on, or actually we finished this up, is studying high resolution spectroscopy between the not involving the science state, just the ground state in the 173 isotope log. So this is something we're doing in collaboration with Arizona State. And we have finished this characterization now, and this chemical production turned out to be a really important tool for this. Ytterbium has lots of isotopes, which is an advantage for science, but it means the spectra is complicated because there are a lot of different isotopes floating around. But by using this technique, we were able to disentangle the different signals and suppress the isotope logs we didn't want in the spectrum. So this was very critical for assigning the spectrum, and we're writing this up right now. Few other interesting advances from our collaborators: 1D laser cooling, detailed branching ratio studies, and we've been working with some theory collaborators to do CP violation sensitivity calculations. There have also been works by Professor Das and by Victor Flambaum and their co-workers looking at this molecule as well. Some future applications. So shifting gears a little bit, one area where this approach would be potentially very useful is looking at exotic isotopes. So one important example is radium, which has a large static octopole deformation, which gives you about a factor of 1,000 increase in hadronic CP violation sensitivity compared to nuclei with atoms with spherical nuclei. This enhancement is a key ingredient in the Argonne National Labs radium electron EDM experiment in atomic radium. And what's exciting is that you can combine this nuclear enhancement with molecular enhancements to get something like 10 to the 6 intrinsic gain in sensitivity to hadronic CP violation. Big challenge is that these heavy nuclei are not stable. These heavy octopole deformed nuclei with spins are not stable. So things like radium, thorium, protactinium isotopes are just challenging to work with. In spite of that, spectroscopy of radium molecules is actually achieved recently, and you'll hear something about that in about 24 hours in Professor Garcia Ruiz's talk, where they actually managed to do spectroscopy on this very challenging molecule. So I encourage you to check out that talk. Radium, because it's an alkaline earth, it won't have these parity doublets. You can think of polyatomics that would have parity doublets, such as with instead of an F, have an OH or an OCH3. Another approach that you could consider is ions, which in this case have some pretty interesting specific features. This ion, RaOCH3+, along with a few others, radium containing molecular ions, was recently created by Andrew Jayich at UCSB, cooled and controlled by co-trapped laser coolable radium ions. And what's interesting about these molecules?
Would you like to wind up in about 5 minutes?
Yep, I can do that.
Thank you.
So these parity doublets that you get from the polyatomic structure enable this GILA ion trap EDM approach, which rely on these parity doublets to do an ion search. You don't need these parity doublets for neutrals; they're very handy, but you really do need them for this ion trap EDM approach. And in this case, this symmetric top structure is very advantageous. And this GILA approach is nice because it's a proven method to reach sort of second scale coherence with systems like this. And a single molecule, a single radium molecule, trapped radium molecule with second scale coherence time would be able to probe new physics. Would be able, and that's just through a combination. You have this combination of molecular and nuclear enhancements. You get very large intrinsic sensitivity increase. And that's how large these enhancements are, that even with one molecule, you could start probing interesting new physics. So this molecule, in this symmetric top molecule and symmetric top molecules in general, the science state, the one where you would do the EDM measurement or the shift moment measurement, in this case, is one where there's 1 unit of rotational quantum about the symmetry axis. So the molecule is sort of rotating in one sense or the other about the symmetry axis. This is called the k=1 state. K is this quantum number that counts the rotational quanta along the symmetry axis. And because it's a rotational excitation, the energy is fairly low. It's around 100 gigahertz or so. And so these symmetric top science states have a lot of advantages. One is that the parity doubling is very small in these states. So you only need something like 10 millivolts per centimeter to polarize the molecule. This particular molecule is open shell, so the only magnetic effects are nuclear effects. So the magnetic moment is very small, so it's very magnetically insensitive. And because of this science state, the energy is so low, you get thermal population. So it should even at 4 Kelvin, there will be some molecules just in this state. So that should make studying it easier. It also has exceedingly long radiative lifetimes that would certainly not be any sort of limitation in the foreseeable future for an experiment like this. There are multiple internal states. If you look at the sort of level structure of the science state, there are multiple states with multiple G factors, multiple splittings, many different transitions you could drive. So there are you could basically do 10 different measurements in this one state to really isolate the shift that you're looking for from some other spurious shift. This molecule is also a good candidate for a proposed technique by Amar Vutha, which you'll hear also in about 24 hours, about looking for doing EDM measurements using clock type, driving clock type transitions. And so we looked at this molecule in some detail, but these advantages are all pretty general to other species, other heavy species, and other ligands, but also other searches. So EDMs, MQMs, etc. And then a completely other direction that you could consider, getting more and more exotic with polyatomic molecules. Earlier, I had said that it sort of doesn't matter what you bond to your atom. It can be F, it can be OH, as long as it just takes one electron away. So you could ask then, why don't you just make it something really interesting, like maybe something with another optically active center in it. So you could have a molecule with multiple sort of laser coolable centers. You could apply larger forces. You could do quantum logic type operations where you could control one center using the other center, etc. Or one of these centers could be something where you could not laser cool or cycle photons, so you could use the other one to do that, etc. We only have theory so far about these molecules, but the short answer is it behaves well. It behaves what you might hope it would behave like. You have 2 quasi-independent centers that you can drive, and that are reasonably well behaved. And you can see this for more details. So we're part of this collaboration to study molecules functionalized with optical cycling centers, to look at theoretically and hopefully eventually experimentally molecules like this. And so that's the conclusion. Thanks again for your time. Thanks to the group. We all meet virtually now, and to all of my collaborators on these different experiments and efforts. And hope you get to come visit the lab one day. And happy birthday.
Thank you very much, Dr. Hatzler, for that excellent talk. Now we are open to questions and comments. I already have a question from Srinivasa Prasanna. he says it's a naive question. What is the role of the extra H nucleus in RaOCH3 plus what? For example, RaOCH2 is the same electronic structure as in number of unpaired electrons, but with a hydrogen nucleus missing. Has it to do with being to produce systems with CH3 more easily in experiment?
Yeah, well, and when in this case, yeah, that's a good question. Yeah, so if I heard the first part, it's wondering about, let's say, like RaOCH2 plus.
Actually, you can see it in your own chat box because this is addressed to everyone. So if you open your chat box.
Okay. Whoops. Hold on, I'm gonna.
If you look at your chat box, the last.
Yeah.
It's a fairly
Share
long
my screen again. Sorry, I had to close my. I was full screen, so I had to close it to see the chat box. But there, it should be back now. And then the chat box went away again. That's okay. I figured it out. Okay. Yeah. So in this case, so yeah, there are a few reasons. So we want for this, you want it to be an ion, to just use this ion trap experiment. For the there's also the advantage that was hinted at in the suggested in the question that yeah, producing this is well, it's already been done. So this is the approach that that Andrew Jayich and his group took at UCSB, was to trap the radium ions, atomic ions, and then flow in methanol, which so the radium replaces one of the H's and you get RaOCH3 plus. But there isn't anything in particular unique about this ligand. You could imagine other ones as well that would give you very similar similar structure. There's a paper written by some of our collaborators at Harvard recently in Physical Review X, looking at actually asymmetric tops, for example, and they classified a number of different ligands, like NH2, for example, where you would get a lot of these same advantages. Yeah, so this in this case, it's really for experimental convenience that you get all these nice features, but you also get sort of a well-behaved production mechanism by reacting with methanol.
Okay. There is one, well, on YouTube, there are no questions. There are only compliments saying that the talk was excellent. So let me convey that to you. And well, there is one question from Vijaya Sahu, says, if triatomic molecules have bent structure, then that is an advantage or disadvantage from the EDM experiment point of view?
Yeah, it probably it depends. It has some features of both, perhaps. Yeah, so one advantage is if, for example, if it's bent in the ground state, then that means that the ground state has these parity doublets, and you would use the ground state for your experiment. Potential disadvantages are, well, one, I mean, it would make the molecule more complicated. It could complicate laser cooling, not necessarily. There are, like in that asymmetric top paper I mentioned earlier, from it's Ben Augenbraun and John Doyle's group. It was recently published in Physical Review X. They examine some bent laser coolable molecules. So they exist. Frequently when they bend, it interferes with the laser cooling, but not always. But if laser cooling is not part of the experiment you're thinking about, like for example in these ion trap experiments, you would laser cooling is not an important part of it. Then that structure is sort of strictly an advantage. So it sort of depends on the details of the experiment.
Good. So then there's one final question from Gerda. He says, well, it's not a question, it's a comment. It says, I will present tomorrow how to produce exotic nuclei and molecules like radium fluoride at CERN. So we'll wait for his presentation in about 24 hours from now. So if there are no more questions from the audience, thank you once again, Dr. Huxler, for that excellent talk. You may unshare your screen if you like. Okay, good. So let me end this session. I think we are at the end of the session after 5 talks. And let me quickly summarize very briefly the 5 talks that were presented. We had a first keynote talk by Pete Schmidt from PTB. He talked about physics of highly charged ions, and his group performed the first coherent laser spectroscopy of argon-13 plus in a cryogenic Paul trap with very high precision. He talked about the results. The next keynote talk was by Professor Budka. He talked about 2 different frameworks for what dark matter could be, whether they are ultralight bosonic particles or axionic quark nuggets. He showed some exotic experimental setups all over the world for this purpose. The third invited talk was by Dr. Per Johnson. He presented development of state-of-the-art computer codes for atomic structure calculations. Such computer programs are in high demand due to advancement in experimental techniques and indeed in astrophysics and medical applications. The fourth keynote talk was delivered jointly by Professor Gordon and Mr. Bondi. They talked about search for new physics beyond the standard model by measuring angular correlations in the beta decay of helium-6. And the final keynote talk was by Dr. Huxler, which we've just listened to. And he described searches for new fundamental physics with much greater sensitivities using polyatomic molecules. So thank all the speakers once again, and it was an excellent session going by the number of questions and comments that arose. So, and thank all the participants for listening in so patiently. Thank the organizers for organizing this workshop. Thank you very much. And I have the pleasure in closing this afternoon session. Thank you. Over to Bindia.
Thank you so much, Professor Sengupta, for chairing this session. And on behalf of FSQT, I would also like to thank all the speakers of this session, Professor Schmidt, Professor Budkar, Professor Johnson, Professor Drake, Bondi, and Professor Huxler. And also thank the chairperson and speakers from our pre-lunch session. So it was a very fruitful day, I hope, for everyone. And we have almost, when we completed everything within time. That's a great achievement for all of us. So with this, we come to an end of this first day, and I hope to see you all tomorrow at 10 a.m. Indian Standard Time. So have a nice day. Goodbye.
And thank you for doing such a great job organizing and running the meeting. So it was a pleasure to participate.
It's a pleasure. Thank you so much, Professor.